Hello there, and welcome to Nightfall Science. Tonight, we drift gently through the quiet question of whether life exists beyond Earth. Let your breathing slow as the stars keep watch above us. Let's begin. The question of life beyond Earth begins with an almost unimaginable amount of space. Earth circles one ordinary star. That star is the Sun, a calm yellow star resting inside the Milky Way galaxy. From the surface of Earth, the Sun appears enormous and powerful, yet among the stars of the galaxy, it is neither unusually large nor unusually bright. The Milky Way contains hundreds of billions of stars. Some are smaller and cooler than the Sun. Others are so large that they could hold millions of suns inside their glowing outer layers. These stars are scattered across a vast spiral of gas, dust, planets, and quiet darkness. Light requires about 100,000 years to cross the galaxy from one side to the other. Even moving at the fastest speed allowed by nature, the journey remains longer than all of recorded human history. The Milky Way is only one galaxy. Beyond it, countless other galaxies drift through the observable universe. Some are graceful spirals like the Milky Way. Some are smooth collections of older stars. Others are small and irregular, shaped by ancient collisions and streams of gas. Every distant point of light may contain billions of stars. Around many of those stars, planets quietly complete their orbits. This immense scale does not prove that life exists elsewhere. Size alone cannot answer the question, but it gently changes the way the question feels. Earth is not standing beside a small empty sea. It is resting within a cosmic ocean filled with stars, worlds, and possibilities. Humanity has explored only the smallest shoreline of that ocean. Radio signals have reached nearby stars, but they have crossed only a tiny fraction of the galaxy. Telescopes have examined distant worlds, but most remain simple points of light. The universe is ancient, enormous, and only partly visible. Within that quiet immensity, one living planet slowly turns around one ordinary star. The search begins there, beneath a sky with more destinations than any traveler could ever reach. The materials needed for life are not unique to Earth. Every known living organism depends on a collection of familiar elements. Carbon forms flexible structures. Hydrogen and oxygen create water. Nitrogen helps build proteins and genetic material. Phosphorus supports the chemistry that allows cells to store and use energy. These elements are found far beyond Earth. Hydrogen is the most common element in the universe. It fills stars, gas clouds, planets, and the thin spaces between them. Oxygen is produced inside stars and scattered outward when stars lose their outer layers or end their lives. Carbon also forms within stars. It later travels into space, becoming part of new clouds, planets, moons, and perhaps living cells. The atoms inside every tree, ocean, animal, and human body belong to this long cosmic history. Many exist because earlier generations of stars create them and release them into the galaxy. Space is not chemically empty. Radio telescopes detect complex molecules inside cold clouds between the stars. These clouds contain water, alcohols, carbon-bearing compounds, and several ingredients related to the chemistry of life. Meteorites also carry organic molecules. Some contain amino acids, which are used by life on Earth to build proteins. These molecules form naturally, without biology. They emerge through ordinary chemistry inside space, asteroids, and young planetary systems. This does not mean that every cloud or meteorite is alive. Organic chemistry is only the beginning. Life requires molecules to organize, reproduce, change, and maintain a stable internal environment. Still, the basic ingredients are widely distributed. A distant planet does not need to borrow its carbon from Earth. A young moon does not need Earth's oceans to receive water. Nature carries these materials through space as stars form, age, and fade. The universe appears capable of preparing the same ingredients in many different places. Whether those ingredients ever awaken into biology remains uncertain. But the cosmic kitchen is large, ancient, and filled with familiar elements. Planets appear to be a natural part of star formation. A star begins within a cold cloud of gas and dust. Gravity slowly draws part of the cloud inward. As the material contracts, the center becomes warmer and denser. Eventually, a young star begins to shine. Not all the surrounding material falls into the star. Much of it settles into a wide, rotating disk. This structure is called a protoplanetary disk. Inside the disk, tiny grains of dust collide. Some bounce apart, others gently stick together. Over long periods, these grains become pebbles, rocks, and larger bodies. Gravity strengthens as the objects grow. Large bodies sweep up material around them. Some become rocky planets. Others gather thick atmospheres and become gas giants. Moons, asteroids, and comets emerge from the same rotating nursery. Astronomers observe these disks around many young stars. Powerful telescopes reveal rings and gaps inside them. Some gaps may be shaped by newborn planets gathering material along their paths. Star formation and planet formation seem closely connected. This discovery changes an older view of the cosmos. Planets no longer appear to be rare accidents circling a few fortunate stars. They appear to be common outcomes of the same process that creates stars. Every system develops differently. The amount of material varies. The temperature of the disk changes with distance. Nearby stars may disturb the forming planets. Young worlds may collide, migrate inward, or be thrown into distant orbits. Some systems become calm and orderly. Others contain planets moving along stretched or tilted paths. Even so, the process repeats throughout the galaxy. Clouds collapse. Stars begin to shine. Dust gathers into worlds. The universe has performed this quiet construction for billions of years. Long before Earth forms, earlier planetary systems already circle older stars. Long after the sun changes, new stars may continue forming from clouds enriched by previous generations. Planets are woven into the life cycle of galaxies. Around countless young stars, dust is still learning how to become a world. Life appears surprisingly early in Earth's history. Earth forms about 4.5 billion years ago. Its earliest period is active and unsettled. Large objects continue striking the young planet. Volcanoes release gases. The surface slowly cools, and liquid water gathers into oceans. The oldest chapters of this history are difficult to read. Earth constantly reshapes its surface. Tectonic plates carry ancient rocks deep underground. Heat, pressure, and erosion erase many early details. Yet the remaining evidence suggests that life is ancient. Clear signs of microorganisms exist in rocks more than 3 billion years old. Other chemical patterns may point to even earlier biological activity, although some interpretations remain uncertain. This means life begins relatively early in the planet's long story. For most of Earth's existence, life remains microscopic. Oceans contain simple cells long before forests, animals, or complex ecosystems appear. These early organisms transform the planet slowly. Some learn to use sunlight as an energy source. Cyanobacteria release oxygen as a byproduct. At first, much of that oxygen reacts with iron and other materials. Eventually, oxygen begins accumulating in the atmosphere. This change opens new paths for biology. Cells gain access to efficient forms of energy. Complex life later becomes possible, although it still requires an immense amount of time. The early appearance of life creates an intriguing possibility. Perhaps life begins easily when conditions are suitable. Given water, energy, useful chemistry, and enough stability, simple organisms may emerge naturally. There is also another possibility. Life may begin on Earth because of an extremely unlikely sequence of events. Its early arrival may not reveal how common it is elsewhere. Humanity has only one known example, making every conclusion uncertain. Earth is both a discovery and a limitation. It proves that non-living matter can become alive. It does not reveal how often that transformation occurs. Still, life does not wait until Earth grows old and quiet. It begins while the planet is young, beneath a sun that shines more softly than it does today. The earliest oceans may carry biology, while the world is still settling into itself. Some planets orbit where liquid water could exist. Astronomers call this region the habitable zone. It is the range around a star where temperatures may allow liquid water on a planet's surface. The zone is sometimes described as the area where conditions are neither too hot nor too cold. But real planets are more complicated than this simple picture. Distance from a star is only one factor. A planet's atmosphere can trap heat. Carbon dioxide, water vapor, methane, and other gases influence surface temperatures. A thick atmosphere can warm a distant planet. A reflective atmosphere or cloud layer can cool a closer one. A planet's mass also matters. A small world may struggle to hold an atmosphere. A larger rocky planet may preserve one for much longer. Rotation, oceans, continents, magnetic fields, and geological activity can all shape climate. Earth rests inside the Sun's habitable zone. Liquid oceans cover most of its surface. Yet the nearby Moon receives almost the same amount of sunlight and remains dry, airless, and exposed. Venus lies closer to the Sun. Its thick carbon dioxide atmosphere traps immense amounts of heat. Mars lies farther away and has a thin atmosphere, leaving its surface cold and dry today. Three nearby worlds experience three very different outcomes. The habitable zone is therefore a useful starting point, not a guarantee. A planet inside it may be lifeless. A planet outside it may hide an ocean beneath ice. Habitability can exist underground, beneath a surface, or inside a moon warmed by gravitational forces. Even the meaning of water requires care. Liquid water supports all known life, but extraterrestrial biology may not follow every earthly rule. Scientists begin with water because it is familiar, chemically useful, and widespread. The habitable zone helps narrow a vast search. It marks places where one important ingredient may remain stable for long periods. Around a distant star, a small world may circle through gentle warmth. Clouds may drift above oceans. Rain may fall across empty stone. Whether anything lives there remains unknown. But the planet rests where water is allowed to stay liquid beneath an alien sky. The most common stars may offer the largest number of homes. Red dwarfs are smaller and cooler than the Sun. They release less light, and many glow with a soft red color. They are also the most common type of star in the Milky Way. Because red dwarfs are faint, their habitable zones lie much closer to them. A potentially temperate planet may complete an orbit in days or weeks instead of 1 year. This closeness makes such planets easier for astronomers to detect. When a planet passes in front of a small star, it blocks a larger fraction of the star's light. The signal becomes clearer. The star also moves slightly under the planet's gravitational pull, allowing instruments to measure its motion. Red dwarfs live for extraordinarily long periods. They use their fuel slowly. While stars like the Sun remain stable for billions of years, the smallest red dwarfs may continue shining for far longer than the universe's current age. This could give life immense stretches of time to emerge and change. Yet these stars also create challenges. Young red dwarfs can produce powerful flares. Bursts of radiation may strike nearby planets. Because habitable worlds orbit so close, they may experience intense stellar activity. Some planets may also become tidally locked. One side constantly faces the star, while the other remains in darkness. Older ideas suggest such worlds might have one burning hemisphere and one frozen hemisphere. Modern climate models offer gentler possibilities. A substantial atmosphere or ocean could transport heat. Winds might carry warmth toward the night side. Water could remain liquid across parts of the planet, especially near the boundary between day and night. The sky there would look very different from Earth's. The star might remain fixed above the same landscape. One horizon could glow in permanent evening. Winds might travel around the globe, joining light and darkness. Red dwarf planets may be difficult homes, but difficulty is not impossibility. Because these stars are so numerous, even a small chance of habitability could represent many worlds. Across the galaxy, countless dim stars continue shining quietly. Close to some of them, small planets turn through endless red daylight. The discovery of exoplanets changes the question forever. For most of human history, planets beyond the solar system remain invisible. Philosophers and astronomers imagine them, but no telescope can confirm their presence. That begins to change near the end of the 20th century. In 1995, astronomers announced the discovery of 51 Pegasi b. It is the first confirmed planet found orbiting a sun-like star. The world is very different from Earth. It is a gas giant orbiting extremely close to its star. Its year lasts only a few Earth days. The discovery surprises astronomers because traditional models place giant planets much farther from their stars. More discoveries soon follow. Some planets are larger than Jupiter, some are smaller than Earth. Some orbit two stars. Others move through systems containing several tightly packed worlds. Space telescopes greatly expand the search. NASA's Kepler mission watches the brightness of many stars. When a planet crosses in front of its star, the star dims by a tiny amount. This method is known as the transit method. Repeated dips reveal the planet's orbital period. The depth of the dip helps estimate its size. Another method measures a star's gentle motion. A planet does not simply orbit a perfectly still star. Both objects move around a shared center of mass. This causes the star to wobble slightly. Astronomers detect that movement through subtle changes in the star's light. This technique is called the radial velocity method. Together, these methods reveal that planets are common. Many stars have them. Multi-planet systems appear throughout the galaxy. Rocky worlds exist. Small planets orbit within regions where temperatures may allow liquid water. The search is no longer based only on imagination. Real worlds now carry names, measured sizes, and known orbits. Among them is the TRAPPIST-1 system, where 7 roughly Earth-sized planets orbit a small red dwarf. Several travel through the star's traditional habitable zone. No evidence currently shows that these planets contain life. Their atmospheres and surface conditions remain subjects of careful study, yet they demonstrate how much can exist around one faint star. A single system can hold several small worlds, each shaped by a different balance of heat, air, rock, and water. The night sky is no longer filled only with distant suns. It is filled with planetary systems. Around stars once seen as simple points of light, entire families of worlds continue moving through the dark. A distant planet's atmosphere can leave a delicate fingerprint in starlight. When a planet passes in front of its star, a small amount of light travels through the planet's atmosphere. Molecules within that atmosphere absorb particular colors. Astronomers separate the light into a spectrum. Dark lines and subtle patterns reveal which wavelengths are missing. Each molecule interacts with light in its own recognizable way. This method is called transmission spectroscopy. Water vapor can leave one pattern. Carbon dioxide leaves another. Methane, sodium, and several other substances may also become visible through careful measurements. The signal is extremely faint. A planet may block only a small fraction of its star. Its atmosphere blocks an even smaller amount. Telescopes must collect many observations and separate the planetary signal from the activity of the star. Clouds can make the task harder. A thick cloud layer may hide gases below it. High-altitude haze can flatten the spectrum, covering chemical details with a pale veil. The James Webb Space Telescope studies some exoplanet atmospheres using infrared light. Its instruments examine worlds ranging from giant planets to smaller rocky candidates. Large gas planets are easier to study because their atmospheres are deep and wide. Rocky planets are much more challenging. Their atmospheres are thin, and their stars can introduce confusing signals. Even so, each observation improves the methods. A planet does not need to be photographed as a bright blue sphere. Its existence and chemistry can be explored through a narrow beam of filtered light. From dozens of light years away, astronomers may eventually estimate whether a world has clouds, water vapor, carbon dioxide, or an unusual chemical balance. The atmosphere becomes a distant message written without words. It records volcanoes, oceans, sunlight, weather, and perhaps biology. Across the darkness, a planet briefly crosses its star. For a few quiet hours, the star's light passes through an alien sky and carries part of that world toward Earth. No single atmospheric gas proves that life exists. Oxygen is often considered an important biosignature because life produces most of the oxygen in Earth's modern atmosphere. Plants, algae, and cyanobacteria release it through photosynthesis. Yet oxygen can also form without life. Ultraviolet radiation can split water molecules. Hydrogen may escape into space, leaving oxygen behind. Carbon dioxide can also be broken apart under certain conditions. Methane attracts attention for a similar reason. On Earth, many microorganisms produce methane. Wetlands, animals, and decaying organic material release it into the atmosphere. Methane can also emerge from geological processes. Reactions between water and certain rocks may create it deep underground. Volcanoes and hydrothermal systems can release carbon-bearing gases without biology. Scientists therefore search for combinations. Oxygen existing beside methane may be more interesting than either gas alone. These molecules react with one another and do not remain together forever. If both appear in large amounts, some continuing process may be replacing them. This condition is called chemical disequilibrium. Earth's atmosphere remains far from chemical balance because life constantly changes it. Organisms remove gases, release new ones, and reshape the surface. A distant atmosphere with an unusual combination of gases might suggest a similar active process. But context remains essential. The star's temperature matters. The planet's age matters. Volcanic activity, surface minerals, oceans, radiation, and atmospheric pressure all influence the chemistry. Even a promising signal may have several possible explanations. Scientists build computer models to test these alternatives. They ask whether geology could create the gases. They study whether the star's light might alter the atmosphere. They compare many possible planetary conditions. The search for life is therefore not a hunt for one magical molecule. It is a patient study of patterns. A living planet may reveal itself through a collection of small clues that make sense only when viewed together. Like a distant landscape seen through morning mist, its shape may emerge slowly rather than all at once. Mars preserves the remains of an older and wetter world. Today, the Martian surface is cold and dry. Its atmosphere is thin, and liquid water cannot remain stable for long across most of the surface. Yet ancient Mars looks very different. Spacecraft images reveal valleys shaped by flowing water. Broad channels cross the landscape. Some regions contain the remains of river deltas, lake beds, and minerals that form in the presence of water. Billions of years ago, Mars has a thicker atmosphere. Rivers may flow across parts of its surface. Lakes gather inside craters, and underground water moves through warm rock. NASA's Perseverance rover explores Jezero crater, where an ancient river once enters a lake. The rover studies layers of sediment within the old delta. On Earth, similar environments can preserve traces of microorganisms. Fine particles settle gently and may trap chemical evidence for immense periods. Perseverance collects carefully selected rock samples. These samples are sealed inside tubes for possible return to Earth by a future mission. Earth laboratories could examine them with instruments too large and delicate to carry on a rover. Scientists could search for complex organic compounds, unusual mineral patterns, and microscopic structures. None of these features would automatically prove ancient life. Rocks can produce shapes that resemble cells. Chemistry can create organic molecules without biology. Every possible clue requires careful testing. Mars also contains organic compounds. The Curiosity rover detects carbon-bearing molecules in ancient sedimentary rocks inside Gale crater. Organic does not mean living. It simply means the molecules contain carbon arranged in particular ways. Still, their survival shows that some ingredients can remain preserved beneath the Martian surface. If life ever begins on Mars, it is most likely simple. It may resemble communities of microorganisms living in water, sediment, or warm cracks underground. That life may disappear as the planet loses much of its atmosphere, or it may retreat deeper beneath the surface, where small amounts of water and protection from radiation could remain. Mars rests close enough to visit, yet its oldest secrets remain sealed inside stone. Across its quiet plains, dry riverbeds still remember the movement of water. Europa may hide a global ocean beneath its frozen surface. Europa is one of Jupiter's largest moons. From a distance, it appears bright and smooth, covered in pale ice crossed by long reddish lines. The surface contains relatively few impact craters. This suggests that it is young and constantly renewed. Beneath the ice, evidence points toward an immense salty ocean. Measurements of Europa's magnetic environment support the presence of an electrically conducting liquid. The most likely explanation is a layer of salty water beneath the frozen shell. This ocean may contain more water than all of Earth's oceans combined. Europa remains warm enough to hold liquid water because of tides. The Moon travels around Jupiter along a slightly stretched orbit. Jupiter's powerful gravity pulls on Europa with changing strength. Other moons also influence its path. Europa flexes as it moves. This repeated bending generates heat inside the Moon. Rock and ice shift gently under pressure, preventing the deep ocean from freezing completely. The seafloor may contain hydrothermal activity. On Earth, hydrothermal vents release warm, mineral-rich water into the deep ocean. Entire ecosystems gather around them without direct sunlight. Microorganisms use chemical energy from the rocks and water. Larger organisms depend on those microbes. Europa might offer a similar energy source, although its conditions remain unknown. Its ice shell may be several kilometers thick. Cracks and ridges suggest that material sometimes moves between the surface and the ocean below. Dark reddish regions may contain salts or other compounds brought upward from deeper layers. NASA's Europa Clipper mission is designed to study the Moon through repeated close flybys. Its instruments examine the ice, gravity, magnetic field, surface chemistry, and possible water plumes. The mission is not built to detect life directly. Instead, it explores whether Europa contains the ingredients and environments that could support it. Liquid water may rest against a rocky seafloor. Chemical energy may flow through the system. Useful elements may move between ice, water, and stone. Far from the warmth of the sun, an ocean remains hidden beneath a silent shell. Above it, Jupiter fills the sky like a vast and slowly turning world. Enceladus releases pieces of its hidden ocean into space. Enceladus is a small icy moon of Saturn. Its surface shines brightly because it reflects much of the sunlight that reaches it. Near its south pole, long fractures cut through the ice. These features are sometimes called tiger stripes. From them, jets of water vapor and tiny ice grains rise hundreds of kilometers above the surface. The Cassini spacecraft flies through these plumes. Its instruments detect water, salts, organic molecules, carbon dioxide, methane, and tiny particles rich in silica. The silica particles are especially interesting. On Earth, similar particles can form when warm water interacts with rock. Their presence suggests that liquid water may circulate through the rocky interior of Enceladus. The hidden ocean may therefore touch a seafloor. Cassini also detects molecular hydrogen in the plume. Hydrogen can form when water reacts with certain rocks in a process called serpentinization. On Earth, microorganisms can use hydrogen as an energy source. This does not show that organisms live inside Enceladus. The reactions can occur entirely through geology, but the moon appears to possess several important ingredients in one place. It has liquid water, it has organic chemistry, it has energy-producing reactions between water and rock. The plumes make Enceladus especially inviting to study. A spacecraft may not need to drill through kilometers of ice. It can pass through material naturally rising from the ocean. Each grain becomes a tiny sample carried into space. Future instruments could search for more complex organic compounds. They might measure patterns in molecules that are difficult to produce through simple chemistry. Researchers could also examine the sizes, structures, and arrangements of carbon-rich particles. Any possible sign of life would require several independent lines of evidence. Contamination would need to be carefully controlled. Non-biological explanations would need to be tested. Enceladus remains a small moon, barely wide enough to stretch across a large country. Yet beneath its ice, a dark ocean may extend around the entire world. Through narrow cracks at the South Pole, that ocean sends a fine mist into Saturn's quiet light. Titan contains rivers, clouds, rain, and seas made from hydrocarbons. Titan is Saturn's largest moon. It is the only moon known to have a thick atmosphere, and its surface pressure is greater than Earth's. The atmosphere consists mostly of nitrogen. High above the surface, sunlight breaks apart methane molecules. Their fragments recombine into more complex hydrocarbons, creating an orange haze that surrounds the moon. Methane behaves on Titan in ways similar to water on Earth. It evaporates from lakes and seas. It forms clouds. It falls as rain. It flows through river channels and gathers in low regions. Near Titan's poles, spacecraft images reveal large lakes and seas filled mainly with liquid methane and ethane. The surface temperature is extremely low. Water is frozen as hard as rock, forming much of the ground and landscape. Mountains may be made of water ice. Pebbles in dry riverbeds may also consist of rounded pieces of ice. Titan's weather carves valleys and reshapes shorelines. It is a familiar cycle created from unfamiliar materials. Life as known on Earth depends on liquid water. Titan's surface lakes are therefore not comfortable environments for terrestrial organisms. Yet the moon is scientifically valuable because it contains rich organic chemistry. Complex carbon-bearing particles settle from the atmosphere onto the surface. They may collect in dunes, lakes, and impact craters. Titan may also hide a liquid water ocean deep beneath its icy crust, in places where impacts or internal heat melt the ice. Water could briefly mix with organic compounds from the surface. Such environments might allow complicated chemistry to develop. NASA's Dragonfly mission is planned to explore Titan using a rotorcraft. The vehicle is designed to fly between locations, examining surface materials and studying how far prebiotic chemistry can progress. Prebiotic chemistry refers to chemical processes that occur before life begins. Titan may resemble no stage of Earth exactly. Its temperature, atmosphere, and liquids are very different. Still, it offers a natural laboratory where the ingredients of life interact across an entire world. Beneath an orange sky, methane rain falls softly onto frozen ground. Dark rivers carry it toward distant seas. Some life may survive without sunlight. Nearly every visible ecosystem on Earth depends on the sun. Plants capture sunlight. Animals eat plants or consume other animals that once depended on plants. For a long time, this seems like the natural pattern for life. Then deep-sea exploration reveals ecosystems around hydrothermal vents. These vents form where seawater enters cracks in the ocean floor. The water is heated by hot rock and rises again carrying dissolved minerals. Some vents release dark, mineral-rich plumes. Others build pale towers and delicate chimneys. No sunlight reaches these depths. Instead of photosynthesis, microorganisms use chemosynthesis. They obtain energy through chemical reactions involving substances such as hydrogen sulfide, hydrogen, methane, and iron. These microbes become the foundation of entire communities. Tubeworms, clams, shrimp, and other organisms gather near the vents. Some animals contain bacteria inside their bodies. The bacteria produce nutrients, while the animals provide a protected environment and access to useful chemicals. The discovery expands the idea of a habitable world. A planet or moon does not always need warm sunlight at its surface. Life may exist beneath ice, underground, or near a rocky seafloor. Gravitational tides can provide heat. Radioactive elements inside rock can release energy slowly. Chemical reactions between water and minerals can support metabolism. Earth also contains microorganisms deep beneath the continents and ocean floor. Some live inside tiny fractures in rock. Their communities may remain isolated from the surface for very long periods. They grow slowly because energy is scarce. Their existence is quiet and difficult to detect. These environments suggest that a planet can appear barren while biology continues below. Mars may contain protected habitats underground. Europa and Enceladus may support chemical energy near their seafloors. Distant exoplanets may hide deep oceans beneath permanent ice. The surface is only one part of a world. Under silent landscapes, heat and chemistry can continue moving. Far from any sunrise, a small cell may still gather energy from stone and water. Life on Earth survives in places once considered impossible. Microorganisms live in highly acidic pools. Others grow in salt deposits, frozen ground, deep rock, or water near the boiling point. These organisms are called extremophiles because they thrive under conditions extreme by human standards. Thermophiles prefer heat. Some live in hot springs and hydrothermal systems. Psychrophiles grow in cold environments. They survive inside polar ice, glaciers, and permanently chilled seawater. Halophiles live in very salty water. Acidophiles tolerate environments with strong acidity. Some microorganisms endure intense radiation. Others survive under enormous pressure at the bottom of ocean trenches. Their adaptations reveal the flexibility of biology. Cells protect their proteins with specialized molecules. Membranes change composition. DNA repair systems correct damage. Metabolism slows when energy becomes scarce. Some organisms enter dormant states. Spores and other resting forms can survive without active growth. When water and suitable temperatures return, biological activity begins again. Tardigrades are small animals known for surviving severe conditions in a dried, inactive state. They are not indestructible, and most cannot remain active in such environments. Their resilience still demonstrates how biological systems can temporarily protect themselves. Extremophiles do not show that life can begin anywhere. Surviving an environment is different from originating within it. Many extreme organisms descend from ancestors that lived under gentler conditions, but they expand the known boundaries of habitability. Liquid water can remain useful across a wide range of temperatures and pressures. Energy can come from sunlight, chemicals, or interactions with rock. Life can become slow, hidden, and remarkably patient. A frozen moon may not be too cold everywhere. A dry planet may hold moisture beneath its surface. A dark ocean may not be empty merely because sunlight never reaches it. Earth teaches that biology does not always occupy the easiest places. It enters cracks, settles beneath ice, and follows faint sources of energy. Wherever water and chemistry continue their quiet work, life may find more room than expected. Life may begin through a long sequence of ordinary chemical steps. Every living cell is extraordinarily complex. It contains membranes, proteins, genetic information, and molecular machines that work together. The earliest life is almost certainly much simpler. Before cells exist, small molecules interact in water, on mineral surfaces, and inside changing environments. Some reactions store energy. Others create larger structures from smaller parts. The study of these processes is called prebiotic chemistry. Scientists investigate how simple compounds can become the building blocks of life. They study amino acids, sugars, fatty molecules, and the components of genetic material. Some of these compounds form naturally in space. Others can emerge through reactions driven by heat, ultraviolet light, lightning, or interactions with minerals. Laboratory experiments show that organic molecules can arise from simple starting materials. The famous Miller-Urey experiment, performed in 1953, circulates gases and water through an apparatus designed to represent possible conditions on early Earth. Electrical sparks provide energy. After several days, the experiment produces amino acids and other organic compounds. Early Earth's atmosphere may differ from the original mixture used in the experiment. Even so, later studies show that useful molecules can form under many possible conditions. The greater challenge is organization. Amino acids do not automatically become living cells. Molecules must begin working together. Some need to store information. Others must speed up reactions or form protective boundaries. Fatty molecules can naturally arrange themselves into tiny spheres in water. These simple membranes resemble bubbles. They can separate an inner chemical space from the surrounding environment. Mineral surfaces may help molecules gather and react. Wet and dry cycles near ponds or volcanic regions may concentrate materials that would otherwise remain scattered. No single pathway has been confirmed as the true beginning of life on Earth. Several environments may contribute different steps. Life may not appear in one sudden moment. It may emerge gradually as chemistry becomes more organized, more stable, and more capable of making copies of itself. Across the young Earth, simple molecules move through water, air, and stone. Within that patient chemistry, matter slowly approaches the boundary between non-living and alive. RNA may once have carried both information and chemical activity. Modern life uses DNA to store genetic instructions. Proteins perform most of the cell's chemical work. This creates a difficult question about the earliest organisms. DNA depends on proteins to copy and maintain it. Proteins depend on information stored in DNA. It is difficult to imagine which system appears first. RNA offers a possible bridge. Like DNA, RNA can carry information through a sequence of chemical units. Unlike DNA, some RNA molecules can also fold into shapes that speed up chemical reactions. These active RNA molecules are called ribozymes. The idea that early life relies heavily on RNA is known as the RNA world hypothesis. In this possible stage, RNA molecules perform roles now divided between DNA and proteins. Some store information. Others help copy molecules or support simple reactions. Over time, DNA may become the main information archive because it is more chemically stable. Proteins may take over many reactions because they can form a greater variety of structures. RNA remains essential in modern cells. It carries messages from DNA. It helps assemble proteins. It regulates genes and performs several other tasks. The ribosome, which builds proteins in every known living cell, depends on RNA at its active center. This ancient molecular role may preserve a faint memory of an earlier biological world. A complete self-replicating RNA system has not been created from simple chemicals under fully natural conditions. Researchers continue studying how RNA building blocks form, join together, and copy themselves. Some experiments show that short RNA-like molecules can grow on mineral surfaces. Others reveal ways that chemical cycles may support copying. The early system may also involve molecules similar to RNA rather than RNA itself. Life's first information carrier could be simpler, later replaced as evolution develops more effective chemistry. The RNA world remains a hypothesis, not a final answer, yet it offers a graceful possibility. Before genes are written in DNA, and before proteins fill the cell, flexible strands of RNA may quietly perform both tasks. In warm pools or sheltered pores, simple molecules may begin recording patterns that survive beyond a single moment. Hydrothermal environments may provide natural chemical laboratories. At the bottom of modern oceans, water moves through cracks in the crust. It reacts with warm rock and returns carrying dissolved minerals. Some hydrothermal vents release extremely hot water. Others, known as alkaline vents, produce cooler fluids rich in hydrogen. Alkaline vents build tall mineral structures. Inside their walls are countless microscopic pores. These pores separate fluids with different chemical properties. Some researchers suggest that such environments could support the earlier steps toward life. Modern cells use differences in electrical charge and proton concentration to store energy. Cell membranes maintain these gradients. Molecular machines then use the gradients to power chemical reactions. At an alkaline vent, natural differences between ocean water and vent fluid can create similar gradients. Mineral walls may act like simple boundaries before biological membranes exist. The pores also concentrate molecules. In the open ocean, useful compounds may drift too far apart to interact often. Inside narrow mineral spaces, they remain closer together. Iron, sulfur, and other minerals can help certain reactions occur. Carbon dioxide and hydrogen may combine into simple organic molecules. These processes resemble parts of ancient metabolism. The vent hypothesis does not explain every step. Genetic information still needs to emerge. Molecules must eventually become enclosed within true membranes. A system tied to a mineral pore must find a way to become independent. Other researchers favor surface environments. Small ponds may experience repeated cycles of wetting and drying. These cycles can concentrate molecules and help them join into longer chains. Ultraviolet light may provide energy. Clays and volcanic minerals may guide reactions. The origin of life may involve several connected settings rather than one location. Materials could form in the atmosphere, arrive on meteorites, collect in ponds, and later continue reacting underground or near the ocean floor. Earth offers many environments, and the young planet remains active for hundreds of millions of years. Across that immense span, chemistry has countless opportunities to repeat, vary, and settle into stable patterns. In the dark pores of warm stone, reactions may continue long before anything resembles a cell. Panspermia suggests that life's ingredients, or life itself, may travel between worlds. Rocks regularly move through the solar system. Large impacts can strike a planet and throw pieces of its surface into space. Some fragments escape the planet's gravity and enter orbit around the Sun. Meteorites found on Earth are known to come from Mars. Their mineral composition and trapped gases match measurements of the Martian surface and atmosphere. This proves that natural exchange between planets occurs. A rock can leave one world, spend thousands or millions of years in space, and later fall onto another. The idea that microorganisms might travel inside such rocks is called lithopanspermia. A thick rock could offer some protection from radiation. Microbes hidden deep within it might remain dormant during the journey. The launch would be intense. The impact that sends the rock into space creates pressure and heat, yet some pieces can escape without melting completely. Arrival creates another difficult stage. Friction heats the rock's outer surface as it enters an atmosphere, but the interior may remain cooler. Laboratory experiments show that some microorganisms and spores can survive parts of these conditions. Whether any organism can endure an entire natural journey remains unknown. Panspermia does not explain how life begins. It only changes where the beginning occurs. If life travels from Mars to Earth, it must still originate somewhere before making the journey. The hypothesis may help explain how life spreads within a planetary system. Early Mars and early Earth exchange more material than they do today. If simple organisms arise on one planet, impacts could carry them to the other. Material may also move between the moons of giant planets, although the journeys are more complicated. A broader form of panspermia imagines life traveling between stars. Such distances are far greater. Radiation, time, and the rarity of successful arrival make this possibility much less certain. Still, organic molecules clearly move through space. Comets, asteroids, and dust carry water and carbon-rich compounds. Young planets receive these materials as they form. The universe naturally transports chemistry from one place to another. A world may inherit part of its chemical beginning from clouds, comets, or neighboring planets. Across silent distances, stone becomes a small vessel carrying the history of one world toward another. The apparent silence of the galaxy is often called the Fermi paradox. The Milky Way is ancient. It contains hundreds of billions of stars and enormous numbers of planets. Some stars form billions of years before the Sun. If intelligent civilizations arise frequently, some could have a very long head start. Even slow-moving spacecraft could cross the galaxy over timescales much shorter than the galaxy's age. This leads to a simple question: where is everyone? The physicist Enrico Fermi is associated with this question after a conversation in 1950 about extraterrestrial civilizations. The word paradox does not mean that two proven facts contradict each other. Humanity does not know how common intelligent life is. It also does not know whether interstellar travel or communication becomes widespread. The paradox is a tension between the apparent abundance of possible worlds and the absence of clear evidence. Many possible explanations exist. Simple life may be common while complex life is rare. Intelligence may evolve only under unusual conditions. Technological civilizations may not last for long periods. They may communicate through methods that remain invisible to present instruments. Their signals may be weak, narrow, or brief. Civilizations might also prefer not to broadcast. They may focus inward, explore through small machines, or communicate using technologies unfamiliar to humanity. Distance creates another challenge. The Milky Way is about 100,000 light-years across. A message from the far side takes tens of thousands of years to arrive. A reply requires the same amount of time. Two civilizations may exist in the same galaxy, but at different moments. One may disappear millions of years before the other develops radio technology. Humanity has produced detectable radio leakage for only a tiny part of cosmic history. The search has also covered only a small fraction of possible frequencies, stars, times, and signal types. The silence may therefore reflect limited listening rather than an empty galaxy. A quiet forest does not contain no life merely because one listener hears nothing during a single minute. The Fermi paradox remains valuable because it organizes questions. It asks scientists to examine biology, technology, time, travel, and the limits of observation. The galaxy appears quiet from Earth, but quiet is not the same as vacant. The Drake equation turns a vast mystery into a series of smaller questions. Astronomer Frank Drake introduces the equation in 1961 while preparing for a scientific meeting about communication with extraterrestrial intelligence. The equation estimates the number of civilizations in the Milky Way that might be capable of communication. It begins with the rate at which stars form. It then considers how many stars have planets, how many planets could support life, how often life begins, how often intelligence evolves, and how long detectable civilizations remain active. The equation does not produce one accepted answer. Several of its values remain deeply uncertain. Astronomers now understand the first terms better than scientists do in 19. Planets are common. Small rocky worlds exist, and some orbit within potentially temperate regions. The biological terms remain much harder. Earth provides the only confirmed example of life. It offers no reliable measurement of how frequently life begins elsewhere. Intelligence is also difficult to define. Many species on Earth solve problems, use tools, communicate, and form complex societies. Only one species builds radio telescopes. The final term may be especially important. A civilization that remains detectable for 100 years contributes far less than one that remains detectable for 1,000,000 years. Detectability may also change. Advanced technology could become quieter and more efficient. A civilization may stop producing strong radio leakage without disappearing. The Drake equation is sometimes misunderstood as a calculator that predicts the number of aliens. Its greater value is conceptual. It separates one overwhelming question into parts that can be studied. Astronomy measures planets and stars. Biology investigates the origin and evolution of life. Social and technological questions explore communication and survival. As knowledge improves, some terms become narrower, others remain open, waiting for new evidence. The equation also reveals how much depends on time. Two civilizations must not only exist in the same galaxy, their detectable periods must overlap. Across billions of years, even a crowded history may feel empty in one particular century. The Drake equation does not resolve the mystery. It gives the mystery a gentle structure, like a constellation drawn between uncertain points. The Great Filter is one possible way to think about rare transitions. Life's history contains many major steps. Non-living chemistry becomes self-replicating biology. Simple cells develop complex internal structures. Multicellular organisms appear. Brains grow more capable. Tool use expands. Technology reaches beyond the planet. Some of these transitions may be common. Others may be extraordinarily rare. The Great Filter is the idea that at least one step between lifeless matter and a long-lived interstellar civilization is very difficult. The difficult step could lie in the past. Perhaps the origin of life is rare. Earth may be unusual because chemistry crosses into biology here. Perhaps simple cells are common, but complex cells rarely appear. On Earth, simple life exists for billions of years before complex multicellular organisms become widespread. Another possibility is that technological intelligence rarely evolves. Evolution does not move toward a predetermined goal. It adapts organisms to local conditions. Bacteria remain highly successful without building tools or cities. The difficult step could also lie later. Technological civilizations may face environmental limits, resource challenges, social instability, or other pressures. This idea is sometimes discussed in dark language, but it can be approached more gently. A filter is simply a transition that few systems complete. It may involve biology rather than disaster. Complex life may require a stable climate, long-lived oceans, plate tectonics, protective planetary conditions, or a sequence of fortunate events. Earth itself experiences many changes. Mass extinctions remove species while opening ecological space for others. Climate shifts reshape evolution. Continents move, oceans change, and the sun gradually brightens. No single history can reveal which steps are typical. The Great Filter remains a framework rather than an observed law. It encourages careful study of every stage. Finding simple life on Mars or Europa would suggest that biology begins in more than one place. Finding complex life in an exoplanet atmosphere would narrow the mystery further. Each discovery would reveal which transitions are easy and which remain rare. Humanity currently stands on one branch of one planet's long biological story. Whether that branch is common or exceptional is still unknown. Across the universe, many worlds may begin the journey, while only a few reach each distant step. Radio waves can carry information across the space between stars. Radio astronomy offers one of the oldest scientific methods for searching for technological civilizations. Natural objects produce radio waves. Stars, pulsars, galaxies, and clouds of gas all create signals through physical processes. A technological signal might differ from natural radio emission in several ways. It could occupy an extremely narrow range of frequencies. It might repeat in a deliberate pattern. It could drift in frequency as a planet rotates and moves around its star. The search for extraterrestrial intelligence, often called SETI, examines the sky for such signals. One early experiment is Project Ozma, led by Frank Drake in 1960. A radio telescope listens to two nearby sun-like stars, Tau Ceti and Epsilon Eridani. No artificial signal is confirmed, but the experiment demonstrates that a systematic search is possible. Modern surveys examine far more stars and much wider ranges of frequencies. The Breakthrough Listen project uses powerful radio telescopes to study nearby stars, the center of the Milky Way, and other targets. Computers search enormous datasets for signals that stand out from background noise. Earth itself creates many false alarms. Satellites, aircraft, mobile communication, radar, and electronic equipment fill parts of the radio spectrum. A candidate signal must be checked from different locations and observed again. A true extraterrestrial transmission should come from a fixed direction in the sky. Human interference often appears in several directions or behaves differently. Most interesting signals disappear after careful analysis. The famous WOW signal is detected in 1977 by the Big Ear radio telescope. It is strong, narrow-band, and lasts 72 seconds. The signal is never observed again, and its origin remains uncertain. It is not accepted as evidence of extraterrestrial intelligence. Its story illustrates the importance of repetition. Science requires a signal that can be confirmed, studied, and separated from every natural or human source. The radio search remains young. Humanity has listened carefully to only a small portion of the sky, across a small portion of possible frequencies, for a brief period. Between the stars, faint signals may pass Earth when no telescope is pointed in their direction. For now, the great radio sky continues to hum with stars, gas, galaxies, and the quiet instruments of Earth. Technology may leave signs other than deliberate messages. A civilization does not need to send a greeting toward Earth to become detectable. Its ordinary activities could alter light, heat, or a planet's atmosphere. These possible signs are called technosignatures. One example is artificial atmospheric pollution. Certain industrial gases are rare or absent in nature. If they appear in the atmosphere of a distant planet, they might suggest technology. Detecting them would be extremely difficult. Telescopes would need to separate a tiny chemical signal from the star's light. Artificial light on a planet's night side is another possibility. Cities on Earth create a visible glow from space. A much larger or brighter civilization might produce a detectable change as its planet rotates. Present instruments cannot see ordinary city lights on distant exoplanets. Future telescopes may search for unusually strong illumination under favorable conditions. Waste heat offers a broader approach. Every technology that uses energy eventually releases heat. An advanced civilization using enormous amounts of power could create excess infrared radiation. Astronomers have searched for stars or galaxies with unusual infrared patterns. Natural dust often produces similar signals, so every candidate needs careful explanation. Large structures built around stars are sometimes called Dyson spheres or Dyson swarms. Physicist Freeman Dyson proposes that an advanced civilization might collect a significant fraction of its star's energy using many orbiting structures. Such a system could absorb visible light and release energy as infrared heat. No confirmed example has been found. Technosignatures could also include laser pulses, unusual spacecraft propulsion, artificial objects crossing stars, or repeating patterns in light. The challenge is imagination. Human searches are shaped by human technology. A civilization far older than Earth's may use methods that do not resemble radio towers, cities, or machines. Still, science begins with measurable possibilities. Astronomers search for effects that known physics allows and instruments can detect. A distant civilization may never speak directly. Its presence might instead appear as a small imbalance in starlight, a strange warmth around a star, or a pattern that nature alone struggles to create. Across the galaxy, technology may leave footprints made not in soil, but in light. Light can carry a message across interstellar space. Radio waves are not the only way a distant civilization might communicate. Visible and infrared light can also travel through the space between stars. A powerful laser could send a narrow beam across enormous distances. If the beam were directed toward Earth, a telescope might detect a brief flash brighter than the natural light of the star at one particular wavelength. This approach is known as optical SETI. Astronomers search for pulses that are extremely short, bright, and regular. Natural objects can produce rapid changes in brightness, but an artificial laser might have a pattern difficult to explain through known stellar activity. A laser message has several advantages. It can carry large amounts of information. Its beam can be focused more tightly than most radio transmissions, reducing the energy needed to reach one chosen destination. The same narrow beam also creates a challenge. A signal aimed at another star may never cross Earth. Even a small error in direction could send it far away from the solar system. The transmitter must also predict where the receiving planet will be when the light arrives. A message sent from 100 light-years away takes 100 years to reach Earth. During that time, stars continue moving through the galaxy. Some searches look for continuous laser light rather than short pulses. A civilization might use lasers for communication, spacecraft propulsion, or navigation. These activities could create artificial-looking features in a star's spectrum. No confirmed extraterrestrial laser signal has been detected. Most observations cover only a limited number of stars and a small fraction of possible wavelengths and pulse patterns. The search remains similar to listening for radio signals. Humanity does not know when a signal might arrive, where it may come from, or which technology creates it. A telescope can watch one star for an hour, while a pulse passes another region of the sky. The silence of one observation reveals little about the entire galaxy. Still, light offers a graceful possibility. A distant intelligence might choose to send not a spacecraft, but a carefully shaped beam. For one brief moment, a star could appear to blink with a pattern created by thought. Small robotic probes may travel farther than biological explorers. Interstellar space is vast, cold, and difficult to cross. Even the nearest star system lies more than 4 light-years away. With present spacecraft technology, a journey there would require thousands of years. Biological travelers need food, protection, stable environments, and life support systems. Machines can be smaller and more patient. A robotic probe can enter a dormant state for much of its journey. It does not need air or sleep. It can survive long periods if its components remain protected from radiation, dust, and extreme temperature changes. Humanity has already sent machines beyond the major planets. Voyager 1 and Voyager 2 travel through interstellar space after completing their journeys past the outer planets. They move quickly by human standards, but slowly compared with the distance between stars. Neither spacecraft is traveling toward a nearby star it will reach within a useful scientific timescale. Future concepts imagine much faster probes. One proposal uses powerful lasers to accelerate a very small spacecraft attached to a reflective sail. Because the craft has little mass, light pressure could push it to a significant fraction of the speed of light. A probe moving at 1/5 light speed could pass through the Alpha Centauri system after a journey lasting a little more than 20 years. Slowing down would be difficult. The probe might simply fly past, collecting images and measurements during a brief encounter. More advanced civilizations may solve such problems in ways that remain beyond current engineering. They could send probes to nearby systems and allow the machines to wait. A probe might study a planet quietly, transmit information home, or respond when it detects technology. Astronomer Ronald Bracewell suggests that advanced civilizations might place automated communication probes near other stars. Such a machine could remain silent until a young civilization becomes capable of noticing it. No evidence shows that such probes exist in the solar system. The idea is scientifically interesting because it avoids some problems of repeated interstellar broadcasting. A local probe could communicate without waiting years between every message. It could preserve information long after its creators change or disappear. Across the galaxy, machines may be better suited than living bodies to long journeys. A small probe could drift between stars for centuries, carrying a quiet library from one planetary system to another. Self-replicating probes could explore a galaxy without moving impossibly fast. A spacecraft that can build copies of itself is often called a self-replicating probe. The idea is associated with mathematician John von Neumann's work on machines capable of reproduction, although he does not design an interstellar probe himself. Such a craft could travel to another star system and use local materials to construct new probes. The copies would then continue toward additional stars. Each individual journey might take centuries or millennia, yet the number of probes could grow as exploration continues. Computer models suggest that a wave of self-replicating machines could spread across the Milky Way in a period much shorter than the galaxy's age. The exact time depends on their speed, reliability, and how long replication takes. This possibility strengthens the question behind the Fermi paradox. If advanced civilizations build such machines, why has humanity not observed one? Several answers are possible. Self-replication may be far more difficult than it appears in theory. A probe needs to find and process raw materials, manufacture delicate components, reproduce complex software, and correct errors without outside help. Tiny mistakes could accumulate across generations. Civilizations may also decide that uncontrolled replication is unwise. They might build limited probes that cannot copy themselves or can produce only a fixed number of descendants. Exploration might be conducted through telescopes rather than physical machines. A sufficiently advanced observatory could study distant planets without traveling to them. Probes could also be small and difficult to notice. An object the size of a grain of dust or a compact instrument hidden among asteroids might escape detection. Human surveys have not examined every region of the solar system in detail. Still, no observation currently requires an artificial explanation. Asteroids, comets, unusual radio signals, and mysterious objects continue to fit natural models when sufficient evidence is gathered. Self-replicating probes remain a thought experiment about what technology might permit. They show that crossing a galaxy does not require one traveler to complete the entire journey. Exploration could move like seeds spreading through a forest, one neighboring system at a time. Over millions of years, patient machines might turn distance into a sequence of smaller steps. Communication between civilizations would unfold very slowly. On Earth, conversations happen almost instantly. A question is asked, and an answer arrives seconds later. Interstellar communication follows a different rhythm. The nearest star system, Alpha Centauri, lies more than 4 light-years away. A message sent there at the speed of light takes more than 4 years to arrive. A reply requires more than 4 additional years. One simple exchange would last almost a decade. For a civilization 100 light-years away, a single reply would take 2 centuries. The senders might never live to hear the answer. Communication would become a project shared across generations. Messages would need to stand alone. They could include explanations, images, mathematics, history, and instructions for understanding the rest. Every transmission might resemble a library, more than a greeting. The long delay also changes the meaning of discovery. A detected civilization is seen in the past. A signal arriving from 1,000 light-years away reveals technology that exists 1,000 years before the moment of detection. The civilization may have changed by the time the message reaches Earth. It may have become more advanced, moved elsewhere, stopped transmitting, or disappeared. Earth appears to distant observers in the same delayed way. An astronomer 100 light-years away currently sees Earth as it was 100 years ago. The light reflected from modern cities and satellites has not yet reached them. Distance divides the galaxy into overlapping layers of history. Two civilizations may exchange messages without ever knowing one another's present condition. Still, slow communication is not meaningless. Humanity reads words written thousands of years ago. Those writers cannot answer, yet their thoughts still cross time. An interstellar message might work in a similar way. It could carry knowledge from a civilization that exists far away or long ago. The exchange would not feel like a conversation beside a table. It would feel like placing a bottle into a very large ocean, knowing that another shore may one day receive it. Mathematics may offer a starting point for a shared language. Two civilizations may have completely different bodies, senses, and cultures. One may communicate through sound, another may use color, electrical signals, chemical patterns, or methods difficult for humans to imagine. Their spoken languages would have no common history. A first message therefore needs a foundation that does not depend on human words. Mathematics is often suggested as that foundation. The properties of numbers do not depend on Earth. Prime numbers remain divisible only by themselves and one wherever they are studied. A sequence of prime numbers could suggest deliberate construction because simple natural sources are unlikely to produce it in a clean pattern. Geometry may provide another bridge. The relationship between a circle and its diameter remains constant. Basic shapes can be represented through numbers and grids. Physics also offers shared reference points. The frequency of radiation emitted by hydrogen can define units of time and length. Hydrogen is abundant throughout the universe, making its properties potentially recognizable. The 1974 Arecibo message uses several of these ideas. It is transmitted toward the globular cluster Messier 13 as a demonstration of communication technology. The binary message contains 1,679 bits. That number is the product of two prime numbers, allowing the data to be arranged into a rectangular image. The image represents numbers, chemical elements, DNA, a human figure, the solar system, and the Arecibo telescope. The message is not expected to begin a practical conversation. Messier 13 is about 25,000 light-years away, and the stars will move significantly while the signal travels. Its value lies in asking how information could be designed for an unknown mind. Even mathematics may not be simple to communicate. The receiver must recognize the signal as intentional, determine its structure, and understand which patterns serve as symbols. A civilization may think in ways shaped by a different environment, yet patterns offer a quiet first step. Before names, stories, and histories can be exchanged, two distant intelligences might begin with counting. One pulse, then two, then three, then five. Across the dark, the order itself could say that someone has chosen to speak. Messages sent from Earth already travel beyond the solar system. Most human radio and television signals are not powerful enough to remain clear across great interstellar distances. They spread outward and weaken. A nearby civilization with very sensitive equipment might detect some powerful radar transmissions, but ordinary broadcasts would be difficult to separate from noise. Humanity has also sent a small number of deliberate messages. In addition to the Arecibo transmission, several projects have directed encoded signals toward nearby stars. These messages often include mathematics, scientific information, music, or representations of life on Earth. Spacecraft carry physical messages as well. Pioneer 10 and Pioneer 11 each hold a metal plaque designed by Carl Sagan, Frank Drake, and Linda Salzman Sagan. The plaque shows human figures, the spacecraft, the solar system, and a map using pulsars to indicate the sun's location. Voyager 1 and Voyager 2 carry the golden records. Each record contains sounds and images selected to represent Earth. The collection includes greetings in many languages, music from different cultures, natural sounds, scientific diagrams, and photographs of life and human activity. Instructions engraved on the cover explain how to play the record and interpret some of its information. The chance that another civilization will find either spacecraft is extraordinarily small. Space is vast, and the voyagers drift through mostly empty regions. The records function partly as messages to humanity itself. They ask what a civilization chooses to say when given one small object and an unknown audience. The result is not a complete portrait of Earth. No collection could contain every culture, species, landscape, or human experience. Instead, it offers a few fragments: ocean waves, birdsong, laughter, footsteps, music, images of cells, families, cities, mathematics, and stars. The records may travel for billions of years if they avoid collisions and severe damage. Long after their power fades, the spacecraft continue moving around the Milky Way. They become silent artifacts from a young technological species. Inside each one rests a golden circle carrying the sounds of rain, wind, and a small world's brief attempt to introduce itself. Intelligence may appear in forms very different from humanity. When people imagine extraterrestrial life, they often picture beings with eyes, limbs, faces, and tools. These features reflect Earth's evolutionary history. Eyes evolve because sunlight is available. Limbs develop within particular environments. Hands help humans manipulate objects, but another species may use tentacles, beaks, trunks, or structures with no earthly equivalent. Intelligence itself is difficult to define. On Earth, dolphins communicate and cooperate. Crows solve problems and make tools. Octopuses explore objects with flexible arms and distributed nervous systems. Elephants show memory, social bonds, and complex behavior. None of these species follows the human path. Their abilities emerge from different bodies and ecological pressures. A technological species on another world may evolve in an ocean. Water would make fire and metallurgy difficult, possibly changing the path toward machines. An intelligent species beneath ice might never see stars. It could develop science by studying tides, chemistry, sound, and the structure of its ocean. Life on a high-gravity planet may remain close to the ground. Life in a thick atmosphere might glide or float. Sensory worlds could also differ. Some organisms may see ultraviolet or infrared light. Others may perceive magnetic fields, pressure waves, electric currents, or chemical gradients. Their understanding of the universe would begin with experiences unfamiliar to humans. Technology may not resemble metal towers and radio dishes. It could grow from biological materials, self-organizing structures, or forms of computation integrated with living systems. Even the distinction between organism and machine may not remain clear. These possibilities are speculative, but they follow a real lesson from biology. Evolution builds from available materials. It does not aim toward one universal body plan. Humanity is one example of intelligence, not its final definition. A distant mind may not look upward with eyes or hold tools with hands, yet it may still measure, remember, wonder, and search. Beneath an unfamiliar sky, thought could arise inside a form that Earth has never prepared human imagination to expect. Most life in the universe may remain microscopic. Earth has supported life for billions of years. For most of that time, the planet contains no animals, trees, or intelligent beings. Its inhabitants are microorganisms. Bacteria and archaea transform the atmosphere, oceans, and rocks. They develop many forms of metabolism and occupy nearly every suitable environment. Complex cells appear later. Multicellular organisms become widespread only during the more recent part of Earth's history. Technological civilization occupies a tiny final fraction. If Earth offers any guidance, simple life may be far more common than complex life. Microorganisms need fewer resources. They reproduce quickly and adapt to changing conditions. They can survive underground, beneath ice, inside rock, or near chemical energy sources. A planet may therefore be alive without appearing green or blue. Its biosphere could exist as a thin layer beneath the soil, or as cells drifting through a hidden ocean. Such life may never produce radio signals. It may never build cities, alter its night side, or send machines into space. Astronomers would need to find it through chemistry. Microbes can change an atmosphere over long periods. They may release methane, oxygen, or other gases. Yet a small or hidden biosphere may create no detectable global signal. Mars could once have hosted microorganisms without leaving obvious fossils. Europa might contain cells in an ocean sealed beneath kilometers of ice. Distant planets could support life that remains invisible, even to advanced telescopes. This possibility softens the meaning of cosmic silence. The absence of messages does not imply the absence of biology. The galaxy could contain many living worlds that never speak. Their organisms may divide slowly in deep water, gather energy from minerals, and continue unchanged for immense stretches of time. They would know nothing of stars, telescopes, or the question asked from Earth. Yet each cell would represent the same remarkable transition. Matter would have learned to preserve a pattern, gather energy, and continue. Across a quiet universe, life may be abundant not as voices in the sky, but as countless small worlds filled with invisible activity. Civilizations may be separated more by time than by distance. The universe is about 13.8 billion years old. The Milky Way begins forming long before the Sun and Earth appear. Many stars in the galaxy are older than the solar system by billions of years. If civilizations arise elsewhere, they do not need to emerge at the same time. One may develop when Earth still contains only simple cells. Another may appear millions of years after humanity is gone. Even if intelligent life is moderately common, the periods during which civilizations are detectable may rarely overlap. A technological phase could be brief compared with the lifetime of a planet. Human radio communication has existed for only a little more than a century. That is a nearly invisible moment beside Earth's 4.5 billion year history. A civilization might use strong radio transmissions for a few hundred years before changing to quieter technologies. It may continue existing while becoming more difficult to detect. Others may choose not to communicate over interstellar distances. The result could be a galaxy with many civilizations spread across different eras. Their monuments, probes, or atmospheric changes might persist after they stop transmitting. But most physical traces gradually fade. Orbits change, surfaces erode, stars brighten, planets lose atmospheres or reshape their crusts. Detecting an ancient civilization would require observing the right world at the right time with instruments sensitive to the right evidence. Earth's own technological signals form a thin, expanding shell. The earliest strong transmissions have traveled only about a century into space. Compared with the Milky Way, this bubble is extremely small. Most of the galaxy has no way to know that humanity uses radio. At the same time, signals from distant civilizations may already be traveling toward Earth, but remain thousands of years away. The universe does not reveal all of its present moments at once. Every observation looks backward. The farther astronomers see, the older the view becomes. Two living worlds can share the same galaxy while remaining hidden behind distance and time. Like ships crossing a dark ocean in different centuries, they may follow similar paths without ever seeing one another's lights. A habitable planet may need more than water and warmth. The traditional habitable zone describes where liquid water could exist on a planet's surface. It is a useful guide, but it does not describe every condition that shapes a living world. Earth remains habitable because many systems work together. Its atmosphere regulates temperature. Oceans store and transport heat. The planet's size allows it to hold gases while maintaining long-term geological activity. The orbit is nearly circular, preventing extreme changes in distance from the Sun. The Sun is also relatively stable. Its brightness changes gradually, rather than violently across short periods. A planet could orbit within a habitable zone and still lack these advantages. Its atmosphere may be too thin to retain heat. It may be so thick that surface temperatures become extreme. Its orbit could be highly elongated, carrying it between intense heat and deep cold. A world covered completely in water may have difficulty cycling important nutrients between rock, atmosphere, and ocean. A dry planet may lose the chemical mobility that water provides. Habitability therefore exists on a spectrum. Some worlds may remain suitable across their entire surfaces. Others may support only narrow regions, seasonal environments, or protected habitats underground. A planet may also move in and out of favorable conditions over geological time. Stars slowly change. Atmospheres escape. Volcanoes release gases. Continents shift, and oceans grow or shrink. Earth itself is not constantly gentle. It experiences global glaciations, major impacts, volcanic episodes, and mass extinctions. Yet life persists through these changes. The resilience of Earth may depend not on perfect stability, but on balance. The planet changes enough to create new environments while avoiding permanent loss of its oceans and atmosphere. This balance could be common. It could also require an unusual combination of factors. Astronomers cannot yet examine all these details on distant planets. They begin with size, orbit, star type, and atmospheric chemistry. Each measurement adds another piece to a much larger picture. A living world may not be defined by one fortunate feature. It may emerge from many quiet systems holding one another in place over billions of years. Plate tectonics may help a planet remain habitable for long periods. Earth's outer shell is divided into large moving plates. These plates drift slowly across the surface. They collide, separate, and slide past one another. The movement is usually measured in centimeters per year. Over millions of years, it reshapes the entire planet. Continents join and divide. Ocean basins open and close. Mountains rise where plates meet. Plate tectonics also moves carbon between the atmosphere, oceans, and interior. Rain removes carbon dioxide from the air through chemical weathering. Rivers carry dissolved material toward the oceans, where some carbon becomes locked into sediments. When one plate sinks beneath another, carbon-rich material can travel into Earth's mantle. Volcanoes later return carbon dioxide to the atmosphere. This process forms part of the long-term carbon cycle. The cycle can help stabilize global temperatures. When Earth becomes warmer, weathering may occur more quickly. More carbon dioxide is removed from the atmosphere, allowing the planet to cool gradually. When temperatures fall, weathering slows while volcanic activity continues returning carbon dioxide. This creates a natural feedback system over immense timescales. Plate tectonics also circulates nutrients. Material from the deep Earth reaches the surface through volcanoes. Old crust is recycled. Mountain building exposes fresh rock to air and water. Whether plate tectonics is necessary for life remains uncertain. A planet with a different geological system might regulate its climate in another way. Some worlds may have a single unbroken outer shell, known as a stagnant lid. Venus appears to have no Earth-like system of moving plates, yet it may still experience large episodes of volcanic resurfacing. Mars has enormous extinct volcanoes, but lacks active global plate tectonics today. Detecting tectonic activity on an exoplanet would be extremely difficult. Atmospheric gases, volcanic compounds, or surface patterns might eventually provide indirect clues. Earth's moving plates are slow enough to escape daily notice. Yet beneath every ocean and continent, the surface is quietly renewing itself. Across geological time, stone participates in the climate of a living world. A magnetic field may protect an atmosphere, but its role is complex. Earth's magnetic field is generated deep inside the planet. The liquid outer core contains moving iron-rich material. Heat, rotation, and electrical currents create a large magnetic region around the world. This region is called the magnetosphere. It interacts with the solar wind, a stream of charged particles flowing outward from the sun. Many particles are redirected around Earth. Some follow magnetic field lines toward the polar regions, where they create auroras. The field helps reduce direct interaction between the solar wind and the upper atmosphere. This may slow atmospheric loss. Mars once possesses a global magnetic field, but it fades early in the planet's history. Without a strong global field, and with lower gravity, Mars gradually loses much of its atmosphere. Solar radiation and charged particles strip gases into space over very long periods. This connection makes magnetic fields appear important for habitability. Yet the story is not simple. Venus has no strong global magnetic field, but it retains a very thick atmosphere. Its gravity, atmospheric chemistry, and interaction with the solar wind produce a different outcome. A magnetic field may offer protection, but it is not the only factor controlling atmospheric survival. Planetary mass matters. Atmospheric composition matters. The star's activity and the rate at which gases are replenished also matter. Magnetic fields could be especially valuable around active red dwarf stars. Nearby planets may experience frequent flares and strong particle winds. A substantial magnetic field might reduce some of this exposure. Detecting such fields from Earth is challenging. Astronomers may search for radio emissions created by interactions between planets and stellar winds. They may also study auroral signals, or the behavior of charged particles around a planet. These methods remain difficult for small, distant worlds. Earth's magnetic field is invisible to human eyes except where it paints faint light across polar skies. It extends far beyond the atmosphere, forming a quiet boundary between the planet and the flowing particles of the sun. Large moons may influence the stability of living planets. Earth's moon is unusually large compared with its planet. It probably forms after a massive collision early in solar system history. A young object roughly the size of Mars strikes Earth. Material from the impact gathers in orbit and slowly becomes the moon. The moon affects Earth in several ways. Its gravity raises tides in the oceans. These tides mix coastal environments and may have influenced early ecosystems. The moon also slows Earth's rotation. A day on the young Earth is much shorter than it is today. Tidal interactions gradually transfer rotational energy, causing the moon to move farther away, while Earth turns more slowly. The moon may also help stabilize Earth's axial tilt. A planet's axial tilt determines how strongly it experiences seasons. Earth's tilt changes over time, but the variations remain relatively limited. Without the moon, computer models suggest that the tilt might change more widely under the gravitational influence of other planets. Large changes could produce stronger climate shifts. However, a large moon is not necessarily required for habitability. Some planets may have stable tilts because of their rotation, orbital arrangement, or the absence of nearby gravitational disturbances. Other planets may support life despite stronger seasonal variation. Moons can also become habitable places themselves. Europa and Enceladus are warmed by tidal forces. Titan maintains a dense atmosphere and active surface chemistry. Large moons orbiting giant exoplanets could contain oceans, atmospheres, and energy sources. No exomoon has yet been confirmed beyond reasonable doubt, although astronomers continue searching. A moon may reveal itself through small changes in a planet's transit timing or through an additional dip in starlight. These signals are delicate and difficult to interpret. Planetary systems are filled with gravitational relationships. Moons pull on planets, planets pull on stars. Orbits shift slowly through time. Earth's moon appears still when viewed from the ground, yet it is part of a long exchange of motion, tides, and stability that has continued since the planet was young. Giant planets may both protect and disturb smaller worlds. Jupiter is the largest planet in the solar system. Its immense gravity influences asteroids, comets, and the orbits of other planets. It is sometimes described as a shield that protects Earth. Jupiter can capture or redirect some objects that might otherwise enter the inner solar system. The comet Shoemaker-Levy 9 provides a dramatic example. After being broken apart by Jupiter's gravity, its fragments collide with the giant planet in 9. The impacts leave dark marks in Jupiter's atmosphere. Yet Jupiter does not simply remove dangerous objects. Its gravity can also alter the paths of asteroids and comets, sending some toward the inner planets. The same powerful influence can protect, redirect, or disturb. Computer simulations show that the architecture of a planetary system matters. The masses of giant planets, their distances from the star, and the shapes of their orbits all affect smaller worlds. If a giant planet moves inward during the early history of a system, it may scatter rocky planets or prevent them from forming. In other cases, migration can deliver water-rich material toward dry inner worlds. Jupiter and Saturn may help shape the structure of the solar system through an early period of orbital movement. Their gravity influences the asteroid belt and the distribution of icy objects beyond Neptune. Earth's history is partly connected to this larger arrangement. A habitable planet does not exist alone. Its environment depends on the gravitational behavior of neighboring worlds. Some systems contain giant planets extremely close to their stars. Others hold several large planets in wide, nearly circular orbits. Astronomers observe an enormous variety of arrangements. There may be no single ideal design. A quiet system could reduce impacts, but occasional impacts may deliver useful materials or create new habitats. Too much stability may not always be necessary. Too much disturbance may prevent long-term development. Around each star, planets participate in a slow gravitational conversation. The shape of one orbit can quietly influence the future of another world. A star's lifetime sets the clock for biological evolution. The Sun has shone for about 4.5 billion years. It is expected to remain in its current stable phase for roughly another 5 billion years. This long period gives Earth time for life to begin, diversify, and eventually produce technological intelligence. Massive stars follow a much faster path. They burn their nuclear fuel rapidly and may live for only millions of years. That may be too little time for complex life to develop on surrounding planets. Massive stars also release intense ultraviolet radiation and end their lives in powerful stellar explosions. Stars smaller than the Sun live much longer. Red dwarfs may remain active for hundreds of billions or even trillions of years. The universe is not old enough for any red dwarf to have completed its full lifetime. Their longevity offers enormous possibilities. A stable planet around a small star could have far more time than Earth. But young red dwarfs often produce strong flares and high-energy radiation. They may strip atmospheres from nearby planets or alter their chemistry. As the star ages, it can become quieter. A planet that survives the active early period may later enter an extremely long era of stability. Orange dwarf stars are sometimes considered promising hosts. They are slightly smaller and cooler than the Sun. They may live longer while producing less intense activity than many red dwarfs. No star type guarantees habitability. Binary systems can also contain planets. Some planets orbit one member of a pair. Others circle both stars at once. The changing light and gravity create more complex conditions, but stable orbits are possible. Life depends on time as much as space. A world may have water and useful chemistry, but its star must remain suitable long enough for biology to continue. On Earth, the transition from simple cells to complex organisms takes billions of years. Elsewhere, it could happen faster or more slowly. Around a long-lived star, evolution may have a very wide horizon. The star rises over each generation, appearing nearly unchanged while life quietly transforms beneath it. The location of a star within the galaxy may influence habitability. The Milky Way is not uniform. Its center contains a dense concentration of stars, gas, dust, and a supermassive black hole. The outer regions are more thinly populated. Some astronomers use the phrase galactic habitable zone to describe regions where conditions may be especially favorable for complex life. Near the center, stars are closer together. This may increase the frequency of nearby supernovae and other energetic events. Strong radiation could affect planetary atmospheres and surface life. Close stellar encounters may also disturb distant comets or planetary orbits. Far from the galactic center, the environment is quieter, but the outer galaxy contains lower concentrations of heavy elements. These elements include carbon, oxygen, silicon, and iron, which are important for rocky planets and complex chemistry. Early generations of stars contain mostly hydrogen and helium. As stars live and die, they create heavier elements and scatter them through space. Later stars form from richer material. The Sun lies roughly 27,000 light-years from the center of the Milky Way. Its region contains enough heavy elements to build rocky planets while remaining far from the most crowded central zones. This does not mean life cannot exist elsewhere. Rocky planets have been detected around stars with different chemical compositions. The boundaries of any galactic habitable zone would also change over time. The early Milky Way is more active and contains fewer heavy elements. As the galaxy ages, more regions become chemically enriched while the rate of violent stellar events changes. A galaxy itself has a history of habitability. Spiral arms, stellar nurseries, ancient star clusters, and quiet outer regions each offer different environments. Other galaxies may follow different patterns. Small galaxies can lose gas. Large elliptical galaxies may contain mostly older stars. Spiral galaxies continue forming new stars inside broad arms. Earth's location is one point within this larger structure. Above the night sky, the Milky Way appears as a pale band. Within that soft glow, stars occupy neighborhoods shaped by the slow evolution of an entire galaxy. False biosignatures make the search for life more careful. A biosignature is a measurable feature that may be produced by living organisms. Atmospheric oxygen, methane, and certain surface colors are common examples. But nature can imitate many biological signs. A planet close to a bright star may lose water from its upper atmosphere. Ultraviolet light splits water molecules into hydrogen and oxygen. The light hydrogen escapes into space more easily, while oxygen remains behind. The atmosphere may become rich in oxygen without any life. Methane can be released through reactions between water and rock. Volcanoes can produce gases that resemble biological activity. A planet's surface minerals may reflect light in colors that look similar to vegetation. Even unusual chemical combinations may arise under conditions not found on Earth. Scientists therefore study the entire planetary context. They examine the host star's spectrum and activity. They estimate the planet's mass, temperature, age, atmospheric pressure, and possible surface environment. A gas becomes meaningful only when its sources and losses are understood. Earth provides a useful example. Modern Earth has abundant oxygen because photosynthetic life replaces it continuously. Without biology, oxygen would react with rocks and other gases and gradually decline. Methane also disappears relatively quickly from the atmosphere. Its continued presence indicates active replenishment. Together, these gases create a stronger sign than either alone. Yet even this combination may not be enough without further evidence. A convincing discovery would likely require multiple observations. Different telescopes might detect several gases. Seasonal changes could be measured. Surface reflections might reveal oceans or broad biological pigments. The findings would need to survive years of testing. Alternative explanations would be compared through climate, chemistry, and geological models. The first possible biosignature beyond Earth may not produce immediate certainty. It may begin as a faint pattern followed by careful debate. Over time, more observations could strengthen or weaken the case. Science approaches extraordinary discoveries slowly because nature is inventive. A lifeless planet can create surprising chemistry. A living planet may reveal itself only after every quiet imitation has been considered. Future telescopes may separate the faint light of Earth-like planets from their stars. A star is vastly brighter than a small rocky world orbiting beside it. From a distant system, Earth would appear as a tiny point reflecting sunlight. The sun would outshine it by billions of times in visible light. Direct imaging requires instruments that suppress the star's glare. One method uses a coronagraph inside the telescope. A carefully designed mask blocks the central starlight while allowing light from nearby planets to reach the detector. Another idea uses a star shade. This would be a large spacecraft flying tens of thousands of kilometers in front of a space telescope. Its flower-like shape would block light from a chosen star, creating a dark shadow around the telescope. Within that shadow, planets could become visible. Direct imaging offers valuable information. As a planet moves around its star, changes in brightness may reveal clouds, oceans, ice, or continents. Light separated into a spectrum can show atmospheric gases. Repeated observations may reveal seasons and rotation. A single point of light can carry a surprising amount of detail. Future observatories are being designed around these goals. NASA has studied the concept of a habitable worlds observatory, intended to search for and characterize Earth-like planets around nearby stars. The project remains in development, and its final design and launch date are not yet fixed. Large ground-based telescopes may also study nearby planets. Their enormous mirrors collect more light, while advanced adaptive optics correct for the blurring caused by Earth's atmosphere. The task remains difficult. Clouds can hide surfaces. Atmospheric gases can overlap in a spectrum. Stellar activity can imitate planetary signals. Still, direct imaging changes the nature of the search. Instead of only measuring a planet's shadow, astronomers may collect light from the world itself. That light begins at a star, touches clouds, water, rock, or ice, and then crosses the space between systems. After traveling for years, a few photons reach a telescope. Inside them rests a faint portrait of a distant world. The first strong evidence of extraterrestrial life may arrive gradually. Popular imagination often presents discovery as a single dramatic moment. A clear message arrives. A spacecraft appears. A distant planet reveals unmistakable life. Scientific discovery is usually quieter. An unusual signal is detected. Researchers examine the instrument and repeat the observation. Other teams study the same target. New models test whether geology, chemistry, or stellar activity can explain the result. Months or years may pass. A possible biosignature could begin as an uncertain atmospheric feature. Later observations might reveal additional gases. The star's activity could be measured more accurately. Climate models might show that oceans are possible. Confidence would grow through many connected pieces. The discovery of simple life within the solar system could follow a similar path. A rover might find unusual organic molecules in Martian rock. A mission to Enceladus might detect complex patterns in material from its ocean. Scientists would examine contamination, geological processes, and every known non-biological alternative. No single molecule or shape would be enough. Evidence would become persuasive when several independent measurements point toward the same explanation. Even a technological signal would require patience. It would need to repeat. It would need to come from the same place in the sky. Observatories in different locations would need to confirm it. Its pattern would have to resist explanations involving satellites, equipment, stars, or natural radio sources. The first announcement may therefore use cautious words: possible, consistent with, difficult to explain naturally. This caution does not make the discovery less meaningful. It allows knowledge to settle on a strong foundation. Humanity's answer to the question may not arrive as a sudden voice from the stars. It may emerge slowly from spectra, samples, repeated signals, and years of careful thought. One day, the balance of evidence may quietly change. The universe will look the same outside the window. Yet Earth will no longer be the only known place where matter has become alive. A living planet does not need to resemble modern Earth. Earth is the only confirmed example of a biosphere, so it naturally guides the search. Astronomers look for rocky planets with moderate temperatures, liquid water, and atmospheres containing familiar gases. Yet Earth itself has taken many forms. For much of its history, the atmosphere contains almost no oxygen. The continents are smaller. The oceans carry different chemistry, and the sun shines less brightly than it does today. A distant observer studying young Earth may not recognize it as the same living world. Its atmospheric signs would differ from those of the modern planet. This history suggests that inhabited worlds may pass through several detectable stages. A young biosphere might release methane without producing much oxygen. A later world might develop photosynthesis and gradually transform its atmosphere. Another planet could remain dominated by microorganisms for billions of years. Its surface might appear brown, orange, purple, or nearly colorless. Life may also exist beneath a global ocean or thick layer of ice. Such a biosphere would barely affect the visible surface. A planet could be biologically active while looking calm and empty from space. Even Earth's modern appearance depends on its clouds. At any moment, much of the surface is hidden beneath weather systems. Oceans reflect light differently, depending on the viewing angle, and vegetation occupies only part of the land. A single distant measurement would reveal little. Astronomers therefore imagine a broad family of inhabited worlds rather than one perfect copy of Earth. Some may be warmer, others may be colder. Some may have shallow seas and wide continents. Others may contain deep global oceans with no exposed land. The search begins with earthly life because it provides real evidence. But the universe may arrange the same essential processes within unfamiliar landscapes. A living world might not appear as a second Earth. It may be a world with its own colors, seasons, chemistry, and long biological memory. Super-Earths may offer environments unlike any planet in the solar system. A super-Earth is generally a planet larger than Earth, but smaller than Neptune. The name describes size or mass, not surface conditions. Some super-Earths may be rocky. Others may hold deep oceans, thick atmospheres, or large envelopes of hydrogen and helium. The solar system contains no planet in this middle range. This makes super-Earths both common in exoplanet surveys and unfamiliar in direct experience. A rocky super-Earth would have stronger gravity than Earth. Its atmosphere could be held more tightly. Mountains might remain lower because gravity pulls material downward more strongly. Volcanoes and tectonic processes could behave differently under greater pressure. A larger interior may retain heat for a long period, supporting geological activity. That activity could recycle gases and nutrients. Yet greater size does not automatically improve habitability. A planet may gather a thick atmosphere during formation. High pressure could create extreme surface conditions or hide the rocky surface beneath deep layers of gas. Some planets in this size range may be mini Neptunes rather than enlarged Earths. Their atmospheres could contain hydrogen, water vapor, methane, and other gases above a deep fluid interior. Determining the nature of a super-Earth requires several measurements. Its radius comes from the amount of starlight blocked during a transit. Its mass may be estimated from the gravitational effect it has on its star or neighboring planets. Mass and radius together reveal average density. A high density suggests a large rocky or metallic component. A lower density indicates more gas, water, or ice. Even density does not provide a complete picture. Several different internal structures can produce similar measurements. Atmospheric observations add another layer. A spectrum may reveal whether the planet has a light hydrogen-rich atmosphere or a denser layer of heavier gases. Some super-Earths orbit within their star's habitable zones. Whether they contain oceans or living surfaces remains unknown. They represent worlds that nature appears to build often, even though the solar system never creates one. Around distant stars, the most common home for life may be a kind of planet that has no local example. Ocean planets could contain water far deeper than any sea on Earth. Earth's oceans cover most of the surface, but they form a thin layer compared with the planet's total size. The average ocean depth is only a few kilometers. A water-rich exoplanet could contain oceans hundreds of kilometers deep. Such a world may form beyond the icy region of a young planetary system and later move closer to its star. Ice and water could make up a large fraction of its mass. From space, the planet might appear almost entirely blue or covered by bright clouds. The absence of continents would create a very different climate and chemical cycle. On Earth, exposed rock reacts with rain and atmospheric gases. Rivers carry minerals into the sea. Volcanoes and plate tectonics exchange material between the surface and interior. A global ocean could limit some of these processes. At great depths, water pressure becomes immense. High-pressure forms of ice may develop even when temperatures remain warm enough for liquid water above. These exotic ice layers could separate the ocean from the rocky interior. If water cannot touch rock, the ocean may receive fewer minerals and less chemical energy. This could make biological development more difficult. Yet not every ocean planet would follow this pattern. A shallower ocean might still contact the seafloor. Volcanic islands could rise above the water. Currents could circulate nutrients, and hydrothermal systems could provide energy. Life on such a world might remain marine throughout its history. Intelligence could evolve beneath the waves. Although the path toward fire, electronics, and spaceflight would differ greatly from the human path. An ocean also creates climate stability. Water stores heat and spreads it through currents. A global sea might protect the planet from sharp temperature changes. Clouds could reflect sunlight, while water vapor warms the atmosphere. The balance would depend on the star, pressure, and ocean depth. From many light years away, an ocean planet may reveal a glint as starlight reflects from liquid. That small flash could come from a surface with no shorelines, where waves have crossed the entire world for billions of years. Rogue planets drift through space without orbiting a star. Most known planets travel around stars, yet gravitational interactions can remove a planet from its original system. During the early formation of planets, large worlds pull on one another. Close encounters may change their orbits dramatically. A planet can be thrown outward with enough speed to escape its star. It then becomes a rogue planet, moving alone through the galaxy. Some rogue planets may also form directly from collapsing gas clouds, in a manner similar to very small stars. Without nearby sunlight, their surfaces would be extremely cold. At first, they seem unlikely places for life, but a planet can contain internal heat. Radioactive elements release energy inside rock. A large world also retains heat left from its formation. A thick atmosphere could slow the escape of this warmth. Hydrogen is especially effective at trapping heat under certain conditions. A rogue planet with a dense hydrogen atmosphere might maintain liquid water at its surface or beneath clouds, even far from any star. More commonly, an ocean could survive beneath a thick shell of ice. The frozen surface would insulate the water below, while heat rises slowly from the interior. This resembles the hidden oceans of icy moons, but without a giant planet providing tidal energy. Life in such an ocean would receive no sunlight. It would depend on chemistry, geothermal heat, or reactions between water and rock. The world would have no sunrise, seasons, or visible stars beneath its ice. Detecting rogue planets is difficult because they reflect little light. Astronomers find some through gravitational microlensing. When a planet passes in front of a distant star, its gravity bends and magnifies the star's light for a short time. The temporary brightening reveals the presence of an otherwise invisible object. Rogue planets may be numerous. Some estimates suggest the galaxy could contain many worlds moving between the stars, although their exact abundance remains uncertain. They expand the idea of where a biosphere might exist. Life may not always need a sunlit sky. Some worlds could carry warm, hidden oceans through interstellar darkness, like quiet ships with no star to call their own. Life around red stars may use colors unfamiliar to earthly forests. Plants on Earth appear green because chlorophyll absorbs much of the red and blue light from the sun, while reflecting more green light. Chlorophyll is well suited to the spectrum reaching Earth's surface. Another star would provide a different balance of wavelengths. Red dwarfs emit much of their energy in red and infrared light. A photosynthetic organism, on a planet around such a star, might use pigments adapted to those wavelengths. Its surface could appear dark red, purple, brown, or almost black. The color would depend on which light the organisms absorb and which they reflect. Photosynthesis is not limited to one pigment. Earth contains several forms of chlorophyll and many accessory pigments. Purple bacteria use molecules called bacteriochlorophylls. Some organisms absorb green light and reflect red or purple tones. Others live beneath layers of water or microorganisms, using the wavelengths that remain available. This variety suggests that alien photosynthesis could follow several pathways. The chemistry still needs an energy source and a way to move electrons. Light provides energy, but the exact molecules may differ. A planet's atmosphere also changes which wavelengths reach the ground. Ozone absorbs ultraviolet light. Water vapor, carbon dioxide, methane, and clouds remove or scatter other parts of the spectrum. An organism evolves beneath the filtered light of its own sky. Astronomers may search for broad changes in surface reflection. Earth's vegetation produces a feature called the vegetation red edge. Leaves strongly reflect near-infrared light, creating a noticeable increase in brightness beyond visible red wavelengths. A distant planet covered in similar life might show a related signal. Alien organisms would not necessarily produce the same edge. Their reflective pattern could appear elsewhere in the spectrum. Minerals and clouds can imitate some color changes, so context remains important. The first distant biosphere may not announce itself through oxygen alone. It might leave a subtle color across continents or seas. Under the soft light of a red star, entire landscapes could be covered by living forms darker than any forest on Earth. Alien life may use chemistry with a different handedness. Many biological molecules can exist in two mirror image forms. These forms are known as enantiomers. They resemble left and right hands. Each contains the same parts, but the structures cannot be perfectly placed on top of one another. Life on Earth shows a strong preference. Proteins are built almost entirely from left-handed amino acids. Sugars in DNA and RNA follow the opposite orientation. This consistent choice is called homochirality. Non-living chemical reactions often produce both mirror forms in roughly equal amounts. Biology selects one and uses it repeatedly. The reason earthly life chooses these particular orientations remains uncertain. The first self-replicating systems may adopt one form by chance. Once established, the choice becomes part of every later biological process. Amino acids with slight imbalances in handedness have also been found in some meteorites. This suggests that space chemistry may create small preferences before life begins. Light, minerals, or physical processes could produce uneven mixtures. On another planet, life might choose the opposite orientation. Its proteins could use right-handed amino acids. Its genetic molecules might be built from mirror versions of earthly sugars. Such organisms would still follow chemistry, but their molecules might interact poorly with terrestrial biology. A nutrient suitable for one system may not fit the enzymes of the other. Chirality could become a useful biosignature. Light passing through or reflecting from a collection of similarly handed molecules can change in a measurable way. This effect is called circular polarization. Vegetation and microorganisms on Earth produce weak polarization patterns because their molecules are arranged asymmetrically. Future instruments might search for similar signals on another world. The measurement would be delicate. Minerals, clouds, and atmospheric scattering also influence polarization. Still, a strong and organized handedness could suggest chemistry shaped by replication and selection. Life may reveal itself not only through the molecules it contains, but through the direction in which those molecules quietly turn. Earth may contain forms of life that remain difficult to recognize. All known organisms share basic features. They use DNA or RNA, build proteins from similar amino acids, and rely on related cellular machinery. This common structure suggests that all known life descends from a shared ancient ancestor. Yet scientists have asked whether Earth could contain a second form of life, with a separate origin. This idea is sometimes called a shadow biosphere. Such organisms might use unfamiliar biochemistry. They could live in environments rarely sampled, or appear similar to ordinary microbes, while remaining chemically distinct. No confirmed shadow biosphere has been found. Studies of microorganisms continue to reveal enormous diversity, but the organisms still fit within the known tree of life. Many microbes cannot be grown easily in laboratories. Scientists detect them by sequencing genetic material directly from soil, water, air, and rock. These methods reveal communities that were once invisible. The possibility remains scientifically interesting, because detection methods often search for familiar features. A test designed to find DNA-based cells may overlook a system that stores information differently. A nutrient mixture suited to common organisms may not support unfamiliar metabolism. The same challenge applies beyond Earth. A mission searching for amino acids, membranes, or DNA-like molecules may find only life that resembles terrestrial biology. Completely different systems could escape notice. However, chemistry creates limits. Any living system needs a way to store information, gather energy, maintain a boundary, and reproduce with variation. These functions may appear through different molecules, but they cannot be absent. Scientists therefore search for patterns rather than exact copies. Complexity, repeated structures, chemical imbalance, selective use of molecules, and organized energy flow may all point toward biology. A second origin of life on Earth would be an extraordinary discovery. It would show that life begins more than once on the same planet. That would suggest the transition from chemistry to biology may be easier than one example currently reveals. For now, every known cell belongs to one immense family. From deep-sea microbes to forests and human beings, life carries variations of an ancient molecular language. Whether another language exists quietly beside it remains an open question. Contamination is one of the greatest challenges in searching for nearby life. Spacecraft are built on Earth, where microorganisms are nearly everywhere. They live in dust, water, skin, air, and tiny spaces inside equipment. Clean rooms reduce contamination, but they do not create complete sterility. If a spacecraft travels to Mars, Europa, or another potentially habitable world, terrestrial microbes could travel with it. This creates two concerns. Forward contamination occurs when Earth material is carried to another world. A hardy microorganism might survive inside a protected part of the spacecraft. If it reaches a suitable environment, it could confuse future searches or interfere with a local ecosystem. Backward contamination refers to material returned to Earth. A sample from Mars or an icy moon could contain unfamiliar chemistry or, in principle, living organisms. The probability and possible consequences must be studied carefully. Planetary protection policies guide mission design. Spacecraft are cleaned using heat, chemicals, filtered air, and strict handling procedures. Missions visiting locations with a greater chance of supporting life follow stronger requirements. Sample return containers are designed to remain sealed through launch, spaceflight, atmospheric entry, and landing. Returned material would be examined inside specialized facilities. Scientists also track contamination by recording which organisms and chemicals are present during spacecraft construction. If a familiar molecule later appears in a sample, researchers can compare it with this record. Contamination control protects both science and planetary environments. A single Earth organism found in Martian soil could be mistaken for local life if its origin were unknown. Likewise, terrestrial organic compounds could imitate an alien biosignature. The search requires patience and careful boundaries. Humanity wants to explore other worlds without erasing the evidence being sought. Every clean instrument becomes part of that effort. Before a spacecraft touches ancient ice or stone, it carries the responsibility to arrive as quietly as possible. A sample from another world could preserve an entirely separate biological history. Mars is one of the most promising places to search for ancient life, because it once has rivers, lakes, and active chemistry. Yet Earth and Mars exchange rocks through impacts. If life is found on Mars, it may share ancestry with Earth. Genetic or molecular similarities could indicate that organisms travel between the planets early in solar system history. A discovery on Europa or Enceladus would offer a different test. These moons form in the outer solar system and remain separated from Earth by very different environments. If life exists in their oceans, it may represent an independent origin. Scientists would compare its chemistry with terrestrial life. Does it use amino acids? Does it prefer the same molecular handedness? Does it store information in DNA, RNA, or something entirely different? Does it use a familiar genetic code? A strong resemblance could point toward shared chemistry or transfer between worlds. Deep differences would suggest that life can begin through more than one molecular pathway. Even simple cells would transform biology. Today, every theory of life is based on a sample size of 1. Earth shows what is possible, but not what is typical. A second biosphere would allow comparison. Features shared by both systems might represent universal solutions. Differences would reveal which parts of earthly biology are historical accidents. Perhaps membranes are always needed, but their chemistry varies. Perhaps information molecules naturally form repeating chains, while the specific building blocks differ. Perhaps evolution produces similar strategies wherever energy and competition exist. A sample return mission or plume-flying spacecraft could provide material for these questions. The first evidence may be microscopic. It could be an unusual pattern of molecules inside one grain of ice. Yet within that grain may rest the answer to whether biology is a singular event or a process repeated by nature. A tiny sample could contain an entire second beginning. The absence of life would also teach something important. A world can possess water, organic molecules, and energy without becoming inhabited. Europa may contain an ocean and rocky seafloor. Enceladus may circulate warm water through minerals. Ancient Mars may hold lakes for long periods. If careful exploration finds no sign of biology, the result would not be empty. It would reveal that suitable ingredients do not automatically create life. The origin of biology may require rare conditions, a particular sequence of reactions, or more time than some environments provide. A lifeless but habitable world would help separate habitability from habitation. This distinction is essential. A house can contain everything needed for a fire, yet no flame ever begins. In the same way, a planet may offer water, carbon, minerals, and energy, while chemistry remains non-living. Negative results are difficult to establish. A mission samples only certain locations. Life may be sparse, buried deeply, or concentrated in environments the instruments cannot reach. Ancient evidence may have been altered by radiation, heat, or geological change. Several missions and many samples would be needed before drawing broad conclusions. Mars demonstrates this challenge. Its surface covers an area similar to all the land on Earth. A few rovers explore only tiny paths across that immense terrain. Finding no life along those paths cannot describe the entire planet. Still, every measurement narrows the possibilities. If organic compounds are absent in one environment, scientists learn how quickly they are destroyed. If certain minerals preserve ancient chemistry, future missions know where to search. Science advances through both discovery and quiet exclusion. A world without life can be as informative as one filled with organisms. It shows which ingredients are insufficient and which transitions remain difficult. Across the solar system, some oceans and riverbeds may hold biology. Others may remain beautifully, completely chemical. Both possibilities belong to the story of how matter behaves among the stars. Intelligence is not the inevitable destination of evolution. Evolution has no fixed goal. It does not guide life toward larger brains, complex tools, or technological civilizations. It simply favors traits that help organisms survive and reproduce within their environments. Bacteria remain among the most successful forms of life on Earth. They occupy oceans, soil, ice, clouds, rocks, and living bodies. Their simplicity does not represent failure. It allows them to reproduce quickly and adapt to changing conditions. Large brains are expensive. The human brain uses a significant portion of the body's energy. It requires long development, reliable nutrition, and protection during childhood. Intelligence becomes useful only when its advantages outweigh these costs. For many organisms, speed, camouflage, efficient digestion, or rapid reproduction may be more valuable. Earth produces complex nervous systems several times. Mammals, birds, and cephalopods each develop impressive abilities through different evolutionary paths. Crows remember faces and solve multi-step problems. Dolphins cooperate and communicate. Octopuses explore objects, open containers, and adapt their behavior. Yet none of these species creates a technological civilization. Human development depends on a rare combination. Hands provide fine control. Upright walking frees them for carrying and making tools. Social groups support learning. Language allows knowledge to accumulate. Fire changes food, warmth, protection, and material processing. No single trait creates technology. They interact across millions of years. A planet may contain intelligent animals without producing radio telescopes. Its oceans could hold creatures with memory and language but no easy access to fire. A world with strong gravity might make flight and space travel difficult. A species may remain well adapted without changing its environment on a planetary scale. Intelligence can exist as awareness, social understanding, navigation, or memory. Technology represents only one expression. Across distant worlds, life may look upward, recognize patterns, and form relationships without ever sending a signal into space. Convergent evolution suggests that nature sometimes discovers similar solutions more than once. Wings evolve independently in insects, birds, bats, and extinct flying reptiles. Eyes also appear through several evolutionary pathways. The structures differ, but they solve the same problem: detecting light and forming information about the environment. Streamlined bodies evolve in sharks, dolphins, and ancient marine reptiles. These animals are not closely related, yet water shapes them towards similar forms. This process is called convergent evolution. When environments create similar challenges, natural selection may favor similar solutions. This raises an intriguing possibility for extraterrestrial life. Alien organisms may be entirely unfamiliar, but some features could still resemble those found on Earth. A world with sunlight may produce light-sensitive organs. An environment containing solid surfaces may favor limbs, gripping structures, or ways to move against gravity. Predators and prey may develop camouflage, speed, armor, or cooperative behavior. Information storage and communication may also emerge repeatedly. Organisms benefit from remembering resources, recognizing danger, and coordinating with others. Yet convergence has limits. Earth's history contains chance events. A mass extinction removes some groups and allows others to expand. A genetic mutation appears in one population and not another. Continents shift, climates change, and ecosystems follow unique paths. Alien life would begin with different molecules, environments, and accidents. The result might combine familiar functions with unfamiliar forms. A flying organism need not have feathers or skin-covered wings. An eye might detect wavelengths invisible to humans. A tool using structure could resemble a trunk, tentacle, mouthpart, or flexible colony of smaller organisms. Convergence may make parts of alien biology understandable. Evolution repeatedly encounters light, motion, competition, cooperation, and the need to gather energy. But it does not need to copy Earth. On another planet, nature may answer the same questions using shapes never produced here. Civilization requires knowledge to accumulate beyond one lifetime. Many animals learn, young birds copy songs. Primates observe tool use. Whales pass behaviors through social groups. These traditions can persist across generations. Human culture develops an unusual degree of accumulation. One generation learns from the previous one, adds new information, and passes a larger collection onward. This process is called cumulative culture. A stone tool can be improved. A method of farming can be refined. A map can preserve journeys made by people who are no longer alive. Language greatly expands this process. Spoken words allow detailed teaching, planning, and storytelling. Writing stores information outside the brain. Libraries, measurements, diagrams, and digital records extend memory across centuries. Technology grows because no individual needs to rediscover every earlier step. A radio telescope depends on mathematics, metallurgy, optics, electronics, and engineering developed by many generations. A distant species may be intelligent but lack this cumulative process. Its individuals might solve difficult problems while their discoveries disappear when they die. Stable social learning could therefore be one of the rare transitions towards civilization. The environment also matters. Materials must be available. Energy sources must be controllable. The species must manipulate objects with sufficient precision. A planet covered by deep ocean may support communication and culture, yet make smelting metal difficult. A world with no dry land might develop advanced biology without industrial technology. Other paths may exist. Organisms could cultivate living materials, use chemical systems, or build structures from minerals near hydrothermal vents. Technology need not begin with fire in every environment. Still, knowledge must somehow accumulate. A civilization is not only a collection of intelligent minds, it is a memory extending beyond each mind. Across generations, ideas become structures, instruments, and shared descriptions of the world. When knowledge begins to outlive its creators, intelligence gains the ability to reshape a planet and eventually to study the stars. Technological civilizations may become quieter as they advance. Earth's early radio technology sends many signals outward unintentionally. Strong television broadcasts, military radar, and communication systems leak some energy into space. This creates the image of a growing radio bubble surrounding the planet. Yet modern communication often becomes more focused and efficient. Signals travel through cables, fiber optics, or narrow beams directed towards satellites. Digital systems can operate with less wasted power. As technology improves, Earth may become harder to detect through accidental radio leakage. A distant civilization could follow a similar path. Its loud period may last only a short time. Before radio, it remains silent to interstellar observers. Later, it may use technologies that produce fewer obvious signals. This creates a narrow window for detection. Two civilizations must exist at similar times, use compatible methods, and observe the correct part of the sky. Deliberate beacons could remain detectable for much longer. A society might transmit powerful signals toward promising stars, perhaps as a scientific project or cultural tradition. But such broadcasting requires energy and motivation. Not every civilization may choose it. Advanced technology could also move away from planetary surfaces. Computing systems might operate in space, where heat can be managed and solar energy collected. Habitats could spread through a planetary system without producing one bright, easily recognized center. Some civilizations may become more visible through waste heat. Others may reduce waste and blend into natural backgrounds. There is no reliable rule that greater advancement creates greater detectability. Human searches often assume that older civilizations use more energy and build larger structures. They may instead value efficiency, stability, or forms of existence that leave little astronomical trace. The galaxy could contain technology hidden not by intention but by refinement. A civilization may begin with towers, engines, and powerful broadcasts. Over time, its activity might soften into narrow beams, small machines, and carefully controlled energy. The most advanced societies may not be the loudest lights in the sky. The Kardashev scale measures civilizations by the energy they can use. Astronomer Nikolai Kardashev proposes the scale in A Type 1 civilization uses energy on the scale available across its home planet. A Type 2 civilization uses energy comparable to the output of its star. A Type 3 civilization operates on the scale of an entire galaxy. Humanity has not reached Type 1. Its total energy use represents only a small fraction of the sunlight, wind, geothermal energy, and other power available on Earth. The scale is not a prediction that every civilization follows the same path. It is a way to connect technology with observable energy. A Type 2 civilization might collect stellar energy using many orbiting structures. A Type 3 civilization could alter the infrared appearance of large regions of a galaxy. Astronomers search for unusual heat patterns that might indicate energy use on these scales. No convincing examples have been found. Natural dust can absorb starlight and release infrared radiation. Star-forming regions, active galactic centers, and old stars all create complex heat signatures. An artificial explanation is considered only after natural possibilities are carefully tested. The Kardashev scale also raises questions about growth. A civilization may not seek continuously increasing energy. Population could stabilize. Technology could become more efficient. Biological beings might change into forms requiring less material and power. Energy use is only one measure of development. Knowledge, longevity, organization, and control of matter may be equally important. A small civilization could possess extraordinary science while using energy gently. The scale remains useful because large energy use must leave physical effects. Energy cannot disappear. It eventually becomes heat. If a society surrounds a star with collectors, the system should glow differently in infrared light. Across the universe, physics provides no perfect concealment from energy balance. Yet the sky so far appears shaped by stars, gas, dust, and galaxies. If great civilizations use entire suns, their traces are either rare, subtle, distant, or unlike the patterns currently imagined. Ancient technology may survive after its builders are gone. Human structures do not last forever. Buildings erode, metals rust, roads become buried, continents move, and sediments cover old surfaces. Across millions of years, most visible signs of civilization would fade. Some traces could remain longer. Mines alter rock layers. Synthetic molecules may persist in sediments. Changes in atmospheric chemistry can leave geological records. Objects placed in stable space environments may endure even longer. A spacecraft in a quiet orbit could survive for millions of years, depending on radiation, collisions, and gravitational changes. Artificial objects on an airless moon would face no rain or wind. Micrometeorites and radiation would still damage them slowly. This leads to the idea of extraterrestrial archaeology. Instead of listening only for active civilizations, scientists can consider evidence left by earlier ones. Unusual objects might exist among asteroids, on moons, or in stable regions where gravitational forces balance. No artificial extraterrestrial artifact has been confirmed. Every candidate requires extraordinary care because natural objects can have surprising shapes, compositions, and orbits. The interstellar object Oumuamua attracts attention after passing through the solar system in 2017. Its brightness changes strongly as it rotates, suggesting an elongated or flattened shape. Its motion shows a small acceleration, not fully explained by ordinary gravitational forces alone. Several natural models are proposed, involving the release of gas or unusual icy materials. No evidence establishes an artificial origin. Its importance lies in showing that objects from other star systems do enter the solar system. Future surveys may find many more. Most will be comets, asteroids, or fragments created by planetary systems. Careful study could reveal their chemistry and origins. If technology ever travels between stars, an artificial object might be found through the same surveys. The discovery would require clear features that nature is unlikely to produce. Until then, the solar system remains a quiet archaeological landscape filled with ancient natural material. Among its moons and asteroids, stones preserve the early history of planets. One day, a clearly manufactured object could join that history. Earth has already transformed its appearance through life. Before life changes the atmosphere, Earth is a different planet. Its early air contains almost no free oxygen. Microorganisms begin photosynthesis, using sunlight to combine water and carbon dioxide into organic material. Oxygen is released as a byproduct. At first, the oxygen reacts with iron in the oceans and minerals on the surface. Layers of iron-rich rock preserve evidence of this change. Eventually, oxygen begins accumulating in the atmosphere during the Great Oxidation Event, more than 2 billion years ago. This transformation alters the chemistry of the entire planet. Many organisms adapted to oxygen-free environments decline or retreat into protected habitats. Other forms of life evolve to use oxygen as an efficient source of energy. The atmosphere later gains enough oxygen to support large, active organisms. Life does not simply adapt to Earth. It changes Earth. Plants alter carbon dioxide levels. Marine organisms build reefs and sediments. Microbes influence clouds, soils, rocks, and ocean chemistry. The modern atmosphere is partly a biological construction. This makes Earth an example of a planet-wide biosignature. A distant astronomer could study the mixture of oxygen, water vapor, methane, and carbon dioxide. The combination might suggest continuous biological activity. Seasonal changes could strengthen the evidence. Carbon dioxide levels shift as plants grow and decay. Surface colors vary with vegetation, snow, and oceans. Human technology adds smaller changes. Industrial gases, artificial light, and radio transmissions create possible technosignatures. Most remain faint from interstellar distances. Earth would not be easy to identify as inhabited. The sun's glare would nearly hide it. Clouds would conceal much of the surface. A distant telescope would collect only a small number of photons. Yet enough careful observations might reveal a world far from chemical balance. The planet's air quietly carries the work of countless organisms. From far away, life may appear not as creatures or forests, but as an atmosphere that refuses to settle into stillness. Earth may already be visible as a living world to nearby observers. Light reflected from Earth travels outward at the speed of light. An observer 10 light-years away sees the planet as it was 10 years ago. An observer 100 light-years away receives light from the early 20th century. The farther the observer, the older the Earth it sees. Most nearby stars cannot resolve the planet as a detailed image with present human technology. A sufficiently advanced telescope could still measure its orbit, size, and atmospheric spectrum. If the observer lies near the plane of Earth's orbit, it may see Earth pass in front of the Sun. During each transit, a tiny fraction of sunlight filters through the atmosphere. Oxygen, ozone, water vapor, carbon dioxide, and methane leave spectral features. The combination could indicate a living planet. Astronomers on Earth have identified nearby star systems from which Earth's transit is or has been visible. Civilizations in those systems would have a favorable geometry for discovering the planet using the same method humans use to find exoplanets. They might not know that intelligent life exists here. Earth's biosphere has been detectable in some form for far longer than its technological civilization. Oxygen becomes abundant hundreds of millions of years before humans appear. A distant observer could identify Earth as biologically interesting while seeing no cities or radio signals. Humanity's strongest deliberate transmissions reach only a limited region. Most nearby systems have never received them. A civilization may therefore know Earth first as a blue world with unusual air. It might watch the planet for centuries, measuring seasons and atmospheric changes. Only much later would faint signs of technology appear. The same sequence may guide human observations elsewhere. First comes the planet, then the atmosphere, then perhaps evidence of biology. Technology may be only the final and briefest clue. Across nearby space, Earth's light continues spreading outward. It carries no written message, yet every spectrum contains a quiet description of oceans, clouds, plants, and breathing life. Contact may begin with observation rather than conversation. The first discovery of extraterrestrial intelligence may not involve an exchanged message. Astronomers could detect a technological effect too distant for practical communication. A planet's atmosphere might contain artificial compounds. A star could show evidence of large-scale energy collection. A repeating laser pulse might arrive from a civilization thousands of light-years away. The signal would reveal intelligence, but any reply would require thousands of years to reach its source. Humanity would know that another civilization exists or once existed, while remaining unable to begin a normal conversation. This would still transform science. It would show that intelligence and technology are not unique to Earth. Researchers would study every available detail. The signal's frequency, timing, polarization, and movement could reveal how it is produced. A structured message might contain mathematics or images. An atmospheric technosignature could offer clues about industry and energy use. Even without communication, the discovery would become a new branch of astronomy. It may also arrive through repeated remote observations. A distant planet could show changing patterns of artificial light. Objects may move around its star in ways suggesting engineering. The evidence would grow gradually until natural explanations become increasingly unlikely. The civilization itself may know nothing about Earth. Its activity may not be intended for anyone else. Humanity would be observing from afar, as astronomers currently observe stars forming, planets orbiting, and galaxies changing. Contact often implies two sides becoming aware of one another. Discovery requires only one side to notice. The universe may offer evidence long before it offers dialogue. A civilization can be present in the data while remaining separated by distance, time, and silence. Humanity may first meet another intelligence, not as a visitor, but as a pattern in light. Across a telescope's detector, a few carefully measured photons could reveal that somewhere beneath another sky, matter has also learned to understand the stars. Some civilizations may choose silence rather than broadcasting. Sending a message into space is technically possible. Humanity already directs radar beams, scientific transmissions, and occasional encoded messages toward distant targets. Yet deliberate communication also requires a decision. A civilization must decide that revealing its presence is worthwhile. It must choose a target, a signal, and a message that may take decades or centuries to arrive. Not every society would make the same choice. Some may listen for a long time before speaking. Others may consider interstellar communication too expensive, too uncertain, or too slow. A civilization could study nearby planets without announcing itself. It might use telescopes to examine atmospheres and technological activity from a distance. This possibility appears in ideas such as the zoo hypothesis. The hypothesis suggests that advanced civilizations may deliberately avoid interfering with younger societies. They might observe quietly, allowing each world to develop independently. There is no evidence that this is happening. The idea remains one possible answer to the apparent silence of the galaxy. It also reflects a familiar human question. Scientists studying wildlife often try to minimize disturbance. Archaeologists preserve delicate sites. Space agencies avoid contaminating potentially habitable worlds. An older civilization might develop similar principles on a much larger scale. Silence may also emerge without any shared policy. Signals weaken with distance. Civilizations may use private communication methods. Their active periods may not overlap. A quiet galaxy does not require every society to agree. It may result from countless individual decisions, technical limits, and differences in time. Humanity often imagines that intelligence naturally wishes to be heard. Another mind may value observation more than announcement. It may turn its instruments toward living worlds and remain patient for thousands of years. Somewhere beyond the solar system, a civilization could know that Earth contains life while choosing not to interrupt its unfolding story. The universe may contain listeners whose presence is expressed only through their restraint. The dark forest idea imagines that uncertainty encourages caution. Two distant civilizations cannot easily understand one another's motives. Messages take years to cross space. Cultures may change before replies arrive. A peaceful signal could be misunderstood, while silence could appear suspicious. This deep uncertainty has inspired the dark forest hypothesis. The idea suggests that civilizations may hide because they cannot know whether others are safe. It is a philosophical scenario, rather than a scientific conclusion. No observation shows that the galaxy contains hostile societies, or that civilizations deliberately conceal themselves. The hypothesis is useful mainly because it highlights the difficulty of trust across interstellar distances. On Earth, trust develops through repeated interaction. People observe behavior, correct misunderstandings, and build shared expectations. Interstellar communication removes much of this process. A message sent to a star 50 light-years away requires a century for one exchange. During that time, governments, languages, and values may change. A civilization could reduce uncertainty by sending information slowly and openly. It might begin with mathematics and astronomy, then share biology, history, and culture. Each message could explain how the sender understands cooperation. A receiver would still need to decide how much to believe. The challenge is not unique to extraterrestrial contact. Human societies have often encountered unfamiliar cultures with incomplete knowledge and unequal power. Those histories offer lessons about patience, consent, humility, and the dangers of assumption. Interstellar distance may create caution, but it also creates safety. A radio message cannot carry an organism or a weapon. It carries information. The receiver can study it before choosing whether to answer. The galaxy's silence may reflect concern, but it may equally reflect rarity, distance, or limited observation. There is no reason to select the most troubling explanation without evidence. Beneath the uncertainty remains a quieter truth. Any civilization capable of listening between the stars has already learned to preserve knowledge across long spans of time. That patience may also shape the way it approaches another world. A confirmed signal would be studied before any reply is sent. The first response to extraterrestrial intelligence would not belong to one individual alone. Astronomers would begin by verifying the detection. Independent observatories would examine the same location. Engineers would check instruments, software, satellites, and local interference. Natural explanations would be tested carefully. Only after repeated confirmation would the question of response become urgent. International groups have discussed general principles for such a discovery. These proposals usually emphasize openness, verification, and broad consultation. No single scientific protocol has the power of a universal law. Countries and institutions may still disagree about what should be said and who should speak. A reply would carry enormous symbolic weight. It might represent Earth to a civilization with no knowledge of human history. Choosing its content would therefore be difficult. A message could begin with simple information. It might describe the solar system, Earth's chemistry, and the biology of its inhabitants. Mathematical patterns could establish structure. Images and diagrams might follow. Human culture would be harder to summarize. Earth contains thousands of languages and many different traditions, beliefs, and ways of life. No short transmission could represent them all. Silence would also be a choice. Even deciding not to answer could shape future possibilities. The delay caused by distance would provide time for reflection. A signal from 100 light-years away cannot receive a reply for at least another century. Humanity would not need to answer during the first week or year. The discovery itself would already be profound. Scientists, philosophers, artists, religious communities, governments, and ordinary people would interpret it in different ways. Some would focus on the science. Others would think about humanity's place in nature. The slow pace of interstellar communication may become an advantage. It allows the world to listen before it speaks. A reply, if one is eventually sent, could become one of the most carefully considered messages in human history. Information theory may help separate a message from noise. Natural signals can be complicated. Pulsars produce precise radio pulses. Molecules create narrow spectral lines. Stars flare, oscillate, and change brightness. A complex signal is not automatically artificial. Scientists would search for structure that suggests deliberate encoding. Repetition is one clue. A sequence that returns at regular intervals may indicate a rotating object, an orbit, or a designed transmitter. The signal's bandwidth also matters. A transmission concentrated in an extremely narrow frequency range may be difficult for some natural processes to produce. Patterns within the signal could carry further evidence. Prime numbers, geometric ratios, or carefully arranged pulses may reveal intention. Information theory studies how information is represented, transmitted, and recovered from noise. A message sent across interstellar space would become distorted. Gas, dust, motion, and instruments could weaken or shift it. The sender might repeat important sections or include error-correcting patterns. Human communication already uses these methods. Spacecraft send data with extra information that allows missing or damaged bits to be reconstructed. An extraterrestrial message may do the same. The first task would be identifying its basic unit. A pulse might represent a number, a boundary, or part of an image. Scientists would search for dimensions that organize the data into meaningful shapes. They might test whether the total number of symbols can be divided into useful grids. Patterns could reveal the message's internal grammar before any symbol is understood. Decoding would probably involve many disciplines. Mathematicians, linguists, computer scientists, physicists, biologists, and historians would examine different layers. Artificial intelligence systems might test possible structures, but human interpretation would remain essential. Meaning depends on context. A diagram of an atom could be mistaken for a star system. A representation of time may use unfamiliar reference points. Understanding could take years. Yet the message would not need to begin with poetry or philosophy. It might begin with repetition and proportion. Out of a stream of pulses, structure would slowly appear. Noise would become number, and number might become the first shared idea between two worlds. Carbon is especially well suited to the chemistry of life. Every known organism is based on carbon. Carbon atoms can form 4 chemical bonds. This allows them to build chains, rings, branches, and 3-dimensional structures. They combine easily with hydrogen, oxygen, nitrogen, sulfur, phosphorus, and many other elements. These properties make carbon useful for storing information and building complex molecular machines. DNA, proteins, fats, sugars, and cell membranes all depend on carbon frameworks. Carbon is also abundant in the universe. Stars create it, and dying stars spread it into space. Astronomers detect carbon-bearing molecules in meteorites, comets, planetary atmospheres, and interstellar clouds. This abundance makes carbon-based life a natural starting point for the search. Some people imagine life built from silicon instead. Silicon lies below carbon in the periodic table and can also form 4 bonds. It is plentiful in rocky planets. However, silicon chemistry is generally less flexible under Earth-like conditions. Silicon bonds strongly with oxygen, often producing stable minerals such as silica. These structures are useful for rocks and computer components, but less suited to the fluid, reversible chemistry needed by cells. Large silicon-based molecules also tend to be less stable in water. This does not prove that silicon can never play a central biological role. An environment with different temperatures, pressures, and solvents might support chemistry unfamiliar to Earth. Life could also use carbon while incorporating large amounts of silicon. Earth organisms already use silica in shells, skeletons, and microscopic structures. Diatoms build delicate glass-like walls. Some plants absorb silicon to strengthen their tissues. Alien biology may combine elements in ways that do not fit simple categories. Still, carbon remains the strongest known candidate. Its versatility is not merely an earthly accident. It follows from the element's fundamental chemistry. The universe contains many possible materials, but some are especially capable of building complexity. In every known living cell, carbon forms the quiet framework on which information, energy, and structure depend. Water may not be the only liquid capable of supporting chemistry. Water has several properties that make it valuable for life. It remains liquid across a useful temperature range. It dissolves many substances and allows molecules to move, meet, and react. Water also participates directly in biological chemistry. Its solid form is less dense than its liquid form, so ice floats. This creates an insulating layer above lakes and oceans instead of freezing them from the bottom upward. Water is abundant in planetary systems. It appears in comets, moons, planets, and interstellar clouds. For these reasons, astrobiology focuses strongly on environments containing liquid water. Other liquids may still support complex chemistry. Ammonia can dissolve several substances and remains liquid at lower temperatures than water under appropriate pressure. A mixture of water and ammonia also freezes at a lower temperature than pure water. This may help maintain hidden oceans inside cold moons. Methane and ethane exist as liquids on Titan's surface. They form clouds, rain, rivers, lakes, and seas. Their chemistry is slower at Titan's low temperatures, but complex organic molecules are present. Some researchers have explored whether cell-like membranes could form in liquid methane. Computer models suggest that certain nitrogen-containing molecules might assemble into stable structures under Titan-like conditions. Whether such membranes exist naturally remains unknown. Liquid carbon dioxide, sulfuric acid, or other solvents have also been considered in unusual environments. Each creates challenges. A solvent must allow useful molecules to remain stable while also permitting reactions. Chemistry that is too slow may struggle to support metabolism. Chemistry that is too aggressive may destroy complex structures. Alien life may not select one pure liquid. It could use mixtures, layers, or changing environments. Even terrestrial cells rely on membranes and internal compartments that create several chemical conditions at once. Water remains the only solvent known to support life. That fact gives it a special place in exploration, yet science keeps the larger question open. On a cold world beneath orange clouds, chemistry may proceed through a liquid that would feel entirely unfamiliar on Earth. Alien metabolism may produce gases that scientists do not yet recognize as biological. Earth's organisms obtain energy in many ways. Plants use sunlight. Animals consume organic material. Microorganisms use hydrogen, sulfur, iron, methane, ammonia, and other substances. Each metabolism changes the environment. Photosynthesis releases oxygen. Methane-producing microbes release methane. Other organisms consume these gases and create new compounds. A distant biosphere may follow reactions uncommon on Earth. Its atmosphere could contain molecules that seem unimportant to current searches. The difficulty is deciding whether a gas is biological. A molecule may be produced by life, geology, sunlight, or several processes at once. Scientists need to understand how quickly it forms and how quickly it disappears. A useful biosignature is often a substance that should not remain abundant without continuous replenishment. The surrounding environment provides the context. A gas detected beside liquid water and another reactive compound may be more meaningful than the same gas on a hot volcanic world. Researchers create databases of possible biosignature gases. They study which molecules different organisms release and how those molecules interact with various stellar spectra. Laboratory experiments test microorganisms in unusual conditions. Computer models simulate atmospheres containing thousands of chemical reactions. The aim is not to predict every alien metabolism. It is to avoid overlooking life simply because it does not produce Earth's most familiar signs. Surface life might also release pigments, waxes, minerals, or airborne particles. Ocean organisms could alter clouds. Microbial communities might create seasonal atmospheric cycles. A biosphere is a network of processes, not one molecule. The strongest evidence may come from several weak signals that fit together. An atmosphere changes with the seasons. A surface color shifts with available light. Reactive gases remain present despite their short chemical lifetimes. Together, the clues could reveal an active planet. Life may write its presence into the air, using an alphabet that scientists are only beginning to imagine. Artificial intelligence helps astronomers search enormous datasets. Modern telescopes collect more information than individual researchers can inspect by hand. A radio survey may contain millions of candidate signals. Planet hunting missions monitor the brightness of thousands or millions of stars. Spectrographs divide light into detailed patterns containing countless features. Machine learning systems can help identify unusual events, They can separate common radio interference from signals that deserve closer study. They can detect small transit patterns, classify stars, and search images for faint objects. These tools are especially useful when the desired signal is hidden inside noise. Artificial intelligence does not remove the need for scientific judgment. A system learns from examples and assumptions chosen by its designers. If the training data are incomplete, unusual natural phenomena may be classified incorrectly. A model may also overlook signals that differ from everything it has seen before. This is important in the search for alien technology. A truly unfamiliar signal may not match the patterns humans label as interesting. Researchers therefore combine automated searches with broader anomaly detection. Instead of asking only for one expected pattern, algorithms can identify data that appear unusual for many reasons. Scientists then investigate the most promising examples. This approach has already revealed rare stars, unexpected radio bursts, and unusual astronomical objects. Most turn out to be natural. That result is still valuable. Every new natural phenomenon improves understanding and makes later searches more precise. Advanced algorithms may also help model exoplanet atmospheres. They can compare observations with large collections of possible temperatures, clouds, and chemical mixtures. The conclusions still depend on the quality of the data. A faint spectrum cannot provide certainty simply because a complex program analyzes it. Machines extend human attention. They allow researchers to listen to more frequencies, examine more stars, and notice subtle patterns. Across vast archives of light and radio waves, an important signal may already exist. A careful algorithm could be the first tool to separate it from the quiet background of the universe. The ethics of contact begin before contact occurs. Humanity already makes choices about other worlds. Spacecraft visit planets, moons, asteroids, and comets. Missions decide where to land, what to collect, and how to avoid contamination. These decisions establish habits that may matter later. If microbial life is discovered on Mars, or an icy moon, scientists will need to consider more than its usefulness. An independent biosphere would have value as a unique natural history. Careless exploration could change or damage it before it is understood. The question becomes even more complex. If intelligent life is detected, a distant civilization may not share human ideas about communication, ownership, privacy, or exploration. Sending a message could affect its development, just as receiving one could affect Earth. There may be no universal ethical rule. Silence preserves distance but prevents exchange. Communication creates knowledge but introduces uncertainty. Humanity would need to consider who participates in the decision. A message sent from Earth would not represent only one country, institution, or generation. It could be received long after its creators are gone. The response may return to descendants living in a very different world. Interstellar communication therefore extends responsibility across time. The content of a message also matters. Technical information may be interpreted differently from music, art, or biology. Detailed descriptions of humanity could reveal both strengths and vulnerabilities. Even a greeting carries assumptions about what should be shared. These questions have no immediate answer because no confirmed contact has occurred. Thinking about them still has value. It encourages cooperation, patience, and awareness of the limits of one perspective. The search for extraterrestrial life is also a study of how humanity behaves when approaching the unknown. A careful explorer does not only ask what can be reached. The explorer also asks how to arrive without causing harm, how to listen without imposing meaning, and how to recognize that another world has a story of its own. The search may continue for generations without a final answer. Astronomy often unfolds across long periods. One telescope discovers a planet, another measures its mass. Years later, a more powerful instrument studies its atmosphere. Future observatories may take direct images and search for oceans, clouds, and biological gases. Missions to Mars and icy moons may return samples or pass through plumes. Radio telescopes will listen to more stars across wider frequency ranges. Each step reduces a small part of the uncertainty. The answer may remain hidden for a long time. This does not make the search unsuccessful. The effort already reveals how planets form, how atmospheres change, and how life survives in extreme environments. It teaches scientists about Earth. Comparing Venus, Mars, and distant planets shows how delicate atmospheric balance can be. Studying extremophiles expands understanding of biology. Listening for technology encourages new methods in radio astronomy and data analysis. The question connects many sciences. Astronomy describes stars and planets. Chemistry explores the path toward complexity. Geology studies the long stability of worlds. Biology investigates how life begins, adapts and transforms its environment. Even without a detected biosphere, every discovery builds a clearer picture of the conditions surrounding life. A future generation may receive the decisive signal. It may find a fossil in Martian stone, a cell inside ocean material, or an atmosphere shaped by distant organisms. The discovery could also remain incomplete. Several planets may appear strongly suggestive without becoming fully confirmed. Science would continue gathering evidence. The universe has existed for billions of years. Its questions do not need to follow the pace of one human lifetime. Each telescope adds a few careful observations to a search that may belong to many generations. Across time, curiosity becomes a shared instrument, passed gently from one group of observers to the next. Earth may be ordinary in some ways and exceptional in others. The principle of mediocrity suggests that Earth does not occupy a uniquely privileged place in the universe. The planet circles one star among hundreds of billions in the Milky Way. The Sun rests far from the galactic center, inside no especially remarkable region of space. The elements forming Earth are common. Rocky planets appear throughout the galaxy. Water exists in clouds, moons, asteroids, comets, and planetary atmospheres. From this perspective, the conditions surrounding life may be repeated many times. Yet Earth's complete history contains a long combination of events. The planet has remained suitable for liquid water across billions of years. Its atmosphere, oceans, geology, and living organisms continually influence one another. Large impacts occur, but none permanently removes the biosphere. The Sun remains stable long enough for complex life to develop. Earth's orbit avoids extreme changes, while geological processes continue recycling material. The rare Earth hypothesis suggests that simple life may be common, while complex organisms require an unusual combination of conditions. A planet may need a stable star, a suitable orbit, useful chemistry, long-lived oceans, geological activity, and a relatively calm planetary system. A large moon or magnetic field may also contribute, although scientists continue debating how essential these features are. No observation yet shows that Earth's combination is rare. Only one inhabited planet is known, making comparison impossible. Some conditions that appear unusual may prove common once better telescopes study more worlds. Others may be less important than currently assumed. Life itself can also stabilize parts of a planet. Organisms alter air, water, soil, and climate. A biosphere may help maintain conditions that allow it to continue. Earth may therefore be ordinary in its ingredients, but unusual in its history. It may be one example among many, or a rare world where several quiet processes remain balanced for an exceptionally long time. Both possibilities fit the evidence presently available. Among countless planets, Earth is the only one close enough to reveal every detail. Its familiarity does not show whether it is typical. It simply gives the universe one known place where oceans, stone, air, and life have remained together beneath the same star. The anthropic principle explains why humanity observes a universe compatible with observers. Certain properties of the universe allow stars, planets, chemistry, and life to exist. Gravity gathers matter into galaxies and stars. Nuclear forces allow stars to create heavier elements. Electromagnetism shapes atoms and chemical bonds. If these properties were very different, complex structures might never form. The anthropic principle begins with a simple observation. Any being capable of studying the universe must exist in a region and era where observers are possible. Humanity should not be surprised to find itself on a planet with conditions suitable for life. An observer cannot appear on a world where observers cannot develop. This idea does not explain how frequently life arises. It also does not show that the universe is designed for biology. It merely warns against drawing conclusions from one location selected by the fact that life exists there. Earth appears remarkably suitable because only a suitable world can produce beings capable of noticing that suitability. The same reasoning applies to time. Humanity lives after several generations of stars enrich the universe with carbon, oxygen, iron, and other heavy elements. It also lives before the sun becomes too bright for Earth's present oceans. Observers naturally appear during a period when their planet remains habitable. The anthropic principle can be useful when considering apparent coincidences, yet it does not replace physical explanations. Scientists still investigate why the laws of nature have their measured values and how planetary systems develop. The principle instead places observation within context. Every view of the cosmos comes from somewhere. Human telescopes are built on one living planet, during one brief stage of its star's life. The universe seen from Earth is therefore both real and locally experienced. Another civilization would observe from a different planet, beneath another star, within another history. Its sky would contain different constellations, but the same underlying laws. Every observer may begin by wondering why its own world appears so perfectly positioned for thought. Life may be common while intelligence remains separated by enormous distances. The Milky Way contains a vast number of planets. Even if only a small fraction develop biology, the total number of living worlds could remain large, yet the galaxy is also immense. Two inhabited planets may be hundreds or thousands of light-years apart. Microbial worlds would produce no deliberate signals. Complex ecosystems might alter atmospheres, but remain difficult to detect. Technological societies may appear only rarely within this wider population. The result could be a galaxy filled with life, but almost empty of conversation. A planet orbiting a distant red dwarf may contain shallow seas and microbial mats. Another may hide organisms beneath ice. A third could support forests or ocean animals without any species developing radio technology. None would announce itself clearly. Humanity's present instruments would struggle to detect most of them. Even an oxygen-rich atmosphere may require many observations. A hidden ocean could remain completely invisible. The number of living worlds and the number of detectable worlds are therefore different quantities. Biology may be widespread, while evidence remains faint. Earth's history illustrates this distinction. For billions of years, the planet contains life but no technology. A distant observer might detect atmospheric changes after oxygen becomes abundant. Before that, Earth would be much harder to recognize. Human radio signals occupy only a tiny final moment. If many worlds follow a similar path, the period of technological visibility may be brief compared with the lifetime of their biospheres. The galaxy could hold an abundance of quiet life. Its oceans may contain cells, ecosystems, and evolutionary histories never seen from Earth. Distance turns those living worlds into small, unresolved points beside their stars. Their silence would not be emptiness. It would be the natural silence of biology continuing without the means or desire to speak across space. The universe may still be early in the history of life. The first stars form relatively soon after the beginning of the universe, but they contain almost no heavy elements. Inside those stars, nuclear reactions create carbon, oxygen, silicon, iron, and other materials needed for rocky planets and complex chemistry. When stars release these elements, later generations form from enriched clouds. Planetary systems become more chemically diverse. Earth appears about 9 billion years after the beginning of the universe. Life may exist on older planets, but many worlds will also form long after Earth. Small red dwarf stars can shine for extraordinarily long periods. The smallest may remain stable for trillions of years, far beyond the current age of the universe. No red dwarf has yet reached the end of its full natural lifetime. This means that much of the potential time available for life lies in the future. New stars will not form forever, but long-lived stars already present may continue providing energy for immense durations. Planets around them could experience evolutionary histories far longer than Earth's entire past. Early stellar activity may challenge life around red dwarfs. Yet if a planet retains an atmosphere and water, later conditions could become calmer. Biology might begin after billions of years, or evolve slowly across timescales difficult to imagine. Humanity therefore observes the universe during an early cosmic era. Technological intelligence may already exist elsewhere. It may also become far more common in the distant future. The apparent silence of the present does not describe all of cosmic history. It describes one moment, viewed from one galaxy, while many stars are still young. The universe is not a completed landscape. Stars continue forming, planets continue cooling, chemistry continues exploring new arrangements. On worlds that do not yet exist, oceans may one day gather beneath unfamiliar skies. The story of life may have begun early, but most of its chapters could still remain unwritten. Extinction does not always end the possibility of complexity. Earth's history includes several mass extinctions. During these events, a large fraction of species disappears within a relatively short geological period. The causes vary. Volcanic activity changes climate and ocean chemistry. Asteroid impacts fill the atmosphere with dust and alter ecosystems. Shifts in temperature and sea level reshape habitats. These events remove branches from the tree of life. They also create new ecological opportunities. After the extinction of non-avian dinosaurs, mammals expand into environments previously occupied by other animals. Over time, new forms emerge. Extinction does not direct evolution toward intelligence. It changes the conditions under which evolution continues. On another planet, frequent global disruptions might repeatedly prevent complex life from becoming established. A calmer world could allow ecosystems to remain stable for longer periods. Yet complete stability may not always encourage innovation. Environmental changes create new pressures and new opportunities. Earth's biological richness arises through a balance between persistence and change. Life survives major transitions because it is distributed across many environments. Microorganisms live underground, beneath oceans, and inside protected sediments. When surface ecosystems change, some forms continue. A planetary biosphere may therefore be more resilient than its visible species. Even if complex organisms disappear, simple life can preserve the possibility of future diversity. This matters when imagining older worlds. A planet may experience several eras of complex life. One technological species could disappear, followed millions of years later by another lineage capable of intelligence. Their histories might never overlap. The second civilization may find only subtle geological traces of the first. Earth has not yet existed long enough to reveal every path that a living planet can take. Its future could contain entirely new ecosystems shaped by descendants of present organisms. On a distant world, evolution may already have repeated the rise and disappearance of complexity several times. A planet's silence in one era may hide a long history of minds that look toward the stars in another. Alien civilizations may understand time very differently. Human life is measured in decades. Projects lasting centuries feel distant, while geological and cosmic timescales are difficult to experience directly. Another intelligent species may live much longer. Its individuals might remain active for hundreds or thousands of years. Such beings could participate personally in interstellar conversations requiring decades between messages. A short-lived species may approach communication differently. Its transmissions would be inherited projects. Each generation would receive replies to questions asked by ancestors. Technology could also change the meaning of lifespan. Biological organisms might extend their lives. They might preserve minds through artificial systems or create machines capable of continuing their goals. A civilization could think in timescales closer to stars than individuals. This would affect exploration. A journey lasting 10,000 years may appear impossible to humans, but manageable to a society designed around long continuity. Probes could move slowly and reliably, reaching neighboring systems without requiring exotic physics. Patience itself could become a form of technology. Civilizations may also experience time at different rates because of environment or computation. Digital minds could slow their activity during long journeys, awakening only when new information arrives. A machine near a cold outer planet might perform thought at a measured pace, using little energy. Such possibilities remain speculative, but they obey known principles. They show how human assumptions shape expectations. Humanity searches for signals repeating over minutes, hours, or years. A civilization operating across millennia might transmit only once every century. Its message could appear as a unique event and never repeat within one observer's lifetime. Another might communicate so rapidly that ordinary instruments record only a smooth burst. The proper rhythm of listening is unknown. Across the galaxy, minds may count moments according to bodies, planets, machines, and traditions unlike those of Earth. A silence lasting 100 years for humanity may be only a pause between sentences for someone else. No discovery would make Earth less valuable. Finding life beyond Earth would show that biology is not unique to one planet. It would enlarge the known community of living matter. Yet it would not make Earth ordinary in any emotional or ecological sense. Earth contains a history found nowhere else. Every species is connected through billions of years of evolution. Forests, coral reefs, deserts, rivers, and microscopic ecosystems represent unique branches of that history. Another living planet would possess its own irreplaceable story. Its organisms would not replace those on Earth, just as discovering another forest does not reduce the value of the first. Instead, comparison would reveal how many forms life can take. If alien biology resembles terrestrial life, the similarity may point toward common chemical principles. If it differs deeply, the discovery would show that nature has more than one path from chemistry to living systems. Either result would deepen understanding of Earth. A second biosphere would help identify which features of life are universal and which belong only to this planet's history. The discovery of intelligence would create an even wider perspective. Humanity would learn that thought, science, and curiosity have emerged elsewhere. Earth would no longer be the only known world from which the universe has examined itself. Still, humanity's responsibilities would remain local and immediate. The existence of distant life would not repair damaged ecosystems or preserve endangered species. It would make the rarity of each biosphere more visible. Even in a universe containing many living planets, the distances between them are immense. No known technology can easily move entire populations between stars. Earth remains humanity's home, source, and oldest living environment. The search outward therefore turns attention inward. The same instruments that study alien climates improve understanding of planetary atmospheres. The same biology that examines extremophiles reveals the resilience and limits of earthly ecosystems. Looking for another living world reminds humanity that it already inhabits one. Beneath the questions of distance and possibility rests a simple fact. Earth is not merely a planet where life can exist. It is a planet where life has existed continuously for billions of years, and where one species has learned to notice. The universe does not need to be crowded for the search to matter. Perhaps life exists on countless worlds. Perhaps simple organisms are common, while intelligence is rare. Perhaps Earth is separated from the nearest biosphere by hundreds of light years. Perhaps the closest living place lies beneath the ice of a nearby moon. Each possibility changes the expected answer, but none removes the value of asking. The search brings together some of humanity's deepest forms of knowledge. Telescopes collect ancient light. Spacecraft touch distant soil. Laboratories examine the chemistry between matter and life. Radio observatories listen for patterns beneath the natural sounds of the sky. Every method reaches into a different part of the question. Even an empty result carries information. A lifeless Mars would teach that water alone is not enough. A sterile ocean beneath Europa would reveal that habitability does not guarantee biology. A silent radio survey would narrow particular frequencies, directions, and times. Science builds understanding from presence and absence alike. The question also changes as instruments improve. Once, planets beyond the solar system exist only in speculation. Now thousands are known. Atmospheres once lie beyond measurement. Today, telescopes begin examining their chemistry. Direct images of Earth-like worlds remain difficult, but future observatories are designed with that goal in mind. The boundary between imagination and observation continues moving. No final answer is required for wonder to remain. The search is already a journey through planetary systems, molecules, oceans, stars, and the long history of Earth. It reveals a universe capable of building immense complexity from simple beginnings. Atoms gather into clouds, clouds become stars, dust becomes planets. On at least one world, chemistry becomes memory, movement, growth, and thought. Whether this happens once or many times, it is already remarkable. The night sky does not need to contain visible cities or arriving messages. Its quiet depth is enough to hold the possibility that life has found other shores. The absence of confirmed evidence is not evidence of permanent solitude. Humanity has searched only a very small part of the universe. Radio SETI has examined limited regions of the sky across limited frequencies and times. Planetary missions have visited only a few locations. Exoplanet telescopes study worlds mostly as shadows, wobbles, or faint atmospheric patterns. The observable universe contains more galaxies than any complete survey can study individually. Even within the Milky Way, most stars have not been examined closely for habitable planets or artificial signals. The search volume is sometimes compared with sampling a small cup of water from Earth's oceans. Finding no fish inside the cup would not show that the oceans are empty. The comparison is imperfect, but it captures the limited scale of present observations. Technology continues expanding that sample. New radio arrays will listen with greater sensitivity. Larger optical telescopes will examine smaller planets. Space missions will study the moons of the outer solar system and collect more detailed information from Mars. Each improvement widens the region in which life might become detectable. There may also be signs that current science has not learned to recognize. Before pulsars are understood, their regular radio pulses appear unusual enough to inspire brief speculation about artificial origins. They are later identified as rapidly rotating neutron stars. Fast radio bursts, quasars, and other phenomena also reveal that nature creates signals beyond earlier expectations. Learning these natural processes improves the search. It teaches astronomers what the universe can produce without technology. A true artificial signal must remain convincing after every natural explanation is considered. The silence measured so far is therefore provisional. It describes what present instruments have not found under particular conditions. It does not close the larger question. Beyond each observed star are many that remain unexamined. Beyond each known planet are atmospheres, surfaces, and possible oceans still hidden from view. The universe has not answered clearly. Humanity has only begun learning how to ask. For now, Earth remains the universe's only confirmed living world. Every known organism belongs to this one biosphere. All forests, oceans, cells, animals, and human cultures exist within a thin layer surrounding a small rocky planet. From space, that layer is nearly invisible. The atmosphere appears as a narrow blue line above the surface. Within it, winds move, clouds form, rain falls, and organisms exchange gases. The depth of the oceans and height of the mountains seem large from the ground. Compared with Earth's diameter, they are small textures across its surface. Life occupies this delicate boundary between rock and space. It reaches several kilometers into the crust and rises into the atmosphere, yet most remains close to the surface. The biosphere is thin, but its history is deep. It begins billions of years before any creature can see the stars. Simple cells change the oceans and atmosphere. Complex organisms follow. Intelligence emerges late. Eventually, instruments are built that can detect planets circling other stars. The living layer begins searching for other living layers. This is one of the strangest features of Earth. Matter formed inside ancient stars becomes rock, water, cells, eyes, and telescopes. Through those telescopes, the planet examines the universe from which its atoms came. There is no confirmed second example yet. That may change through a sample, a spectrum, a signal, or a discovery not presently imagined. Until then, Earth carries the full known weight of life. It is one small world, orbiting one star, within one galaxy among countless others. Across its night side, people look upward from different continents and ask the same quiet question. The sky offers no final reply. It simply continues shining, leaving room for curiosity to remain. The universe may be silent because life is rare. It may be silent because distance is large. It may be silent because civilizations speak in unfamiliar ways, appear in different eras, or choose to remain quiet. These explanations are not mutually exclusive. Different regions of the galaxy may hold different answers. One moon may contain simple cells. One planet may support complex ecosystems. Another system may once have contained technology, now faded from view. The universe rarely needs one explanation for every place. Diversity is already one of its clearest patterns. Stars vary in mass, color, and lifetime. Planets range from scorched rock to frozen giants. Moons contain atmospheres, oceans, volcanoes, and fields of ice. Life, if it appears elsewhere, may be equally varied. The phrase "are we alone" sounds like a question with only two answers. Reality may be more subtle. Humanity could be alone within the solar system, but not within the galaxy. It could share the galaxy with microorganisms while remaining the only technological species nearby. Other civilizations may exist, but remain separated from Earth by time. A clear yes or no may eventually become a map of different kinds of life, distance, and history. For now, the question remains open. An open question is not an empty one. It contains observations, experiments, missions, and generations of thought. It guides telescopes toward small planets and spacecraft toward hidden oceans. It encourages biology to examine its own beginnings. It asks humanity to consider what intelligence means and how one world should approach another. The silence above Earth is therefore not the end of the story. It is the quiet space in which the search continues. And perhaps, somewhere around a distant star, another living world rests beneath its own night sky. There, Another form of awareness may also look into the darkness and wonder whether thought has appeared anywhere else. The distance between the two questions may be immense, yet the questions themselves would already form something shared. The universe is larger than any single world can fully understand. It contains stars that shine for millions of years and others that may glow for trillions. It contains planets hidden in darkness, oceans sealed beneath ice, and chemistry moving patiently through clouds of gas and dust. On one small planet, that chemistry becomes alive. It learns to grow, adapt, remember, and eventually ask where else the same transformation may have occurred. No confirmed answer has yet crossed the space between stars. But the search has revealed that planets are common, water is widespread, and the ingredients of life exist throughout the cosmos. It has shown that life on Earth survives in heat, cold, salt, darkness, stone, and deep water. It has uncovered hidden oceans and thousands of distant worlds. Each discovery makes the universe feel not smaller, but more richly connected. The atoms of living cells come from ancient stars. The light entering a telescope may have traveled for decades, centuries, or billions of years. The search for life joins these two histories. It connects the chemistry inside a cell with the evolution of galaxies. For now, humanity remains beside one known ocean of life, listening across a much larger cosmic sea. The water is calm, the horizon is distant, and beyond it, the possibilities continue quietly beneath the stars. But for now, there is no need to travel any farther. Let the distant planets soften into small points of light. Let the hidden oceans become still beneath their coverings of ice. Let the galaxies continue their slow turning without needing to be followed. Your journey has crossed ancient stars, quiet worlds, and the long history of living Earth. Now let your shoulders rest. Let your breathing become gentle and unhurried. There is no question that needs to be answered tonight. The universe has carried its mysteries for billions of years, and it can continue carrying them while you sleep. The stars will remain above the night. The planets will continue along their distant paths. Radio waves will move silently between systems, and soft light will keep traveling through the dark. You have gone far enough for one night. Allow every thought to drift away, like a small cloud passing through a wide and peaceful sky. And if you are still awake and would like to keep drifting, another quiet journey is waiting for you on screen. If these calm nights bring you a little peace, you are always welcome to return and wander gently through the cosmos again, one drifting mind at a time. Sleep well, and good night.